I shall say good morning as well. The bios of all of those people should be in the Dropbox. So if you see somebody in the Dropbox whose bio says they work on something related to what you work on, again, feel free to email them because the emails are all in there, or to send them chats saying, you know, hi, I'm Fred. I work on the same thing as you do. Do you want to have an email conversation about it? And of course, this is a virtual version of a meeting that we've run now for several years, and we've never run it virtually before. But what we're going to try and do is to make the virtual experience as close as we can to the experience of being at the course. And that's difficult and it may fail. But when we run the courses, you know, lectures are lectures. Everybody knows what lectures are. And you can get a certain amount of information across in the lecture. But there are two aspects to the course that really, in our experience, have worked very well. And one of them is the breaks. So we previously brought in a bunch of people from around the country, around the world, and then during the coffee breaks, they all get to know each other. And because they work on obviously related topics, there's always somebody in the room who's working on something that you care about. So we're going to try and replicate that on Zoom. And this is the bit I don't know if it'll work or not. And what you're going to find is every time we have a break, you're going to get dumped into a breakout room with a set of people. We've tried to set it up so it's A, randomized, so you should get to meet most of the other people on the course at some point. And B, nearly everybody should get access in one of those to me, to David, and to Shona. So at some point during the course, you'll find yourself in a breakout room with one of us. Not everybody will, because that's the nature of random mixing. So in those sessions, feel free to say, you know, I work on this and I'm interested in that and what do you think and things like that. But also take that opportunity to network with each other and talk with each other. And we'll gauge how that goes during the session. And if it's a total disaster and everybody just logs out and leaves a blank screen and goes read their emails, then we'll abandon it because it's not working. But you can read emails anytime, right? You can look at your Twitter feed and see what President Trump is up to anytime. So try and make an effort to engage in this interaction networking aspect and let's see how that works. And then feedback to us. If you really find it doesn't work, that's fine, we'll change it. But I'm hopeful that it will. And then the other aspect that's worked really well is the interactiveness of the practical sessions. So the way those are set up is, they're all slightly different, but in essence, we pose you a problem. We show you the parameters of that problem. And then we dump you back in a breakout room with a bunch of people, the ones you would have met in the break just before that session. And you're supposed to figure out the answer to that particular question. And then come back into the main room and we discuss it. And I'll pick on breakout room 4 and say, what did you think? And then breakout room 4 will say, so I'll try breakout room 5 and they'll say, yeah, we think this is the answer to the question. And again, we'll see how that goes. When it's live, that goes really well. I hope it'll work equally well in this virtual format, but we'll see. And again, if it doesn't work for you, kind of either send Ricky a chat or just stick your hand up and say, look, this doesn't work for me, so I'm not going to do it. No, that's fine. We can work it out as we go along. So I really want you to try and be interactive, not just to be a quiet audience sitting there being told stuff. You know, you can do that in lots of other formats. What we want you to do is during the lectures to interfere, to raise your hand or to turn on your volume and say, look, I don't understand what you're saying. That makes no sense to me. Can you explain that point again? And we'll try and do that as interactively as we can. Obviously, at some point, if we have a dominant individual who wants to tell us their life story, then we'll cut you off. But I think we all understand how this process works, and people, I hope, will ask lots of questions, but pertinent and sensible questions. And then the masterclass. This is a masterclass, and I think you know what that means, right? If you were to sign up to a violin masterclass, you would not expect somebody to say, this is a fiddle, this is how you put your fingers on the frets, and you make music from it. And the same with the bioenergetics masterclass. We're going to assume you understand the chemiosmotic theory. We're going to assume that you understand the basics of how energetics in cells work. And what we're going to try and do is to take you the step beyond that and really look at some of the assumptions that you may be using or you may not be using, and give you our view of how you should view different things. That might be the thermodynamics of some of the reactions that are going on. It might be the use of the oxygen electrodes and the seahorses that people are using. It might be techniques for measuring membrane potential. But we're going to, I hope, challenge you, and hopefully when this works, make you realize that you're actually doing something wrong in some of the things you do, and you would do better to do it this other way. And then if you don't agree, you can kick back and say, but my supervisor has told me this is a good way to do it, and we can discuss why your supervisor is an idiot and why you should change to somebody else. The timings, because everybody's online and some people will be dropping out to make cups of coffee and have bio breaks and make breakfast. We don't necessarily expect that everybody will be here all of the time, but we are also in control of the timing. So I'm going to be relatively lax with that. So if a lecture overruns a bit or runs a bit short, we'll just do that and then move on to the next session. So if you do drop out and drop back in, I don't guarantee that we'll be running to exact time. We'll try not to overrun stupendously, because that's unfair on you and on us. But we'll also be fairly flexible. So if you drop out and drop back in again, we won't necessarily be exactly where you expected us to be in the program. We'll do what we can to keep it roughly on time. And if I go on too long, Ricky will wave at me and say, you know, quiet down, this is time to move on from this. The drop boxes, so I mentioned the drop boxes, you'll find the bio. Also, what we plan to do is to put up the lecture PowerPoints and the practical PowerPoints the day before. So you have a chance to review what's coming up. And also you can go there now and you can pull down David's lecture, which is going to follow this. So you can follow it through on his PowerPoint or on the PDF, mine are in PDFs. And in particular, when we come to the practical sessions, it's a good idea to do that because the mechanics of it, and I'll be running the first of those later on during the day, the mechanics of it will be that I will pose you a question, which will have a slide associated with it, and then you'll be hauled off and dropped into a breakout room. And we don't have any easy way for you to see that screen and to see that breakout question. So you need to have it with you. So it might be a good idea when we come to the practical sessions in particular to follow through on your own deck so that you have the right screen in front of you, which is the one we just left, leaving you in the breakout room with four other people with a question. If you get lost, you can always, I think you can do this, Ricky, you can chat from a breakout room to Ricky, is that true? You
Yes.
can't?
Yes.
Shona's shaking no, and Ricky said yes. You're muted, Shona. Shona, you're muted.
I am no longer muted. In a breakout room, you can only chat within the breakout room. You can't chat to the main session, but you can go to the main session.
And back again?
Yes.
Okay, I didn't hear that first part.
So we will leave the question screen up in the main session. So if you do get lost, you can go back to the main session, see what it is, then go back to the breakout room and find it. And hopefully, of course, there'll be a team of people and somebody else will have it and will share their screen. And you can share screens within your breakout room. There's also reading lists on there. So we broke those into things we thought were kind of important. And I hope most of you have looked at that and had a chance to review some of the reviews that we set. But we also put some optional things in there, which we don't necessarily expect you to read, but if you're puzzled by something that I say in my lectures, there may be one of the references there which covers it, and you can go read that in between the days so that you can the next day say, I still don't understand it. I read what you said in page 17 and it still doesn't make any sense. Can you explain it? And we can either do that in one of the question answer sessions, or you could do it in a breakout room if you bump into me, or you could ask the other people in the breakout room Dr. Brand said this thing, I don't get it. What was he on about? And hopefully one of the other people can tell you what they think. And also during the breakout sessions for the practicals, we're going to seed the rooms with members of my lab. So various of the people are lab members, postdocs, research associates in my lab. And they will mostly be spread out amongst the breakout rooms for these practical sessions. And their role there is not to tell you the answers or to give you a tutorial, but if you get stuck and the clock is ticking and nobody knows what on earth they're supposed to be doing or how to get at this question, then that planted person can say, you know, have you thought about looking at it this way? And that might jog you onto a track that's more successful. But of course, you can also just chat to them and say, you know, what do you do? And what's interesting in your life? And what science are you interested in? And then the other thing in the Dropbox is the programs. So there are 2 or 3 Excel sheet programs which you'll need during the practical sessions. I think they haven't yet been uploaded to the Dropbox, but they'll be uploaded the day before. And we really recommend that you download them. They're Excel sheets, so I hope everybody can therefore open them and run them. And those will be interactive in David and Shona's practical sessions where you need to enter data into that and then things happen in that spreadsheet. And often you're asked to interpret what it was that happened in a breakout session or live in the practical session itself. So download those Excel sheets beforehand, make sure they work. And if they don't work, call Ricky, who will sort it out and work out how to get you a copy that does work. Okay, I'm just checking my list. I think that's all I really felt was necessary to say. David, Shona, is there anything else we should say? And then participants, any queries or questions, anything that you'd like to raise before we begin the main session?
Yeah, I think you've covered most of it. We'll see how it goes.
I think just really quick, Zoom is very awkward for having the sorts of informal interruptions and discussions that we typically have in person. But as Martin said, it's really helpful and it's really important, and it makes the course really valuable to do exactly that. So please feel free to interrupt by audio. You can raise your hand on the screen. You can raise your hand using the Zoom function. Please get our attention if you have a question or a comment that you think is relevant to the discussion. That interactivity is truly important. So don't feel like you are being rude to interrupt. That's built into the course.
And use the chat as well. So if you can't get our attention, put it in the chat and we'll try and monitor that. And one of the 3 or 4 of us, Ricky and the 3 presenters, should pick that up and then break into the lecture and say, there's this question on the chat. And then during the sessions, can you all mute when you're not actually asking a question so we don't hear your mum come in and say, what are you doing and why haven't you done your washing yet? But then obviously remember to unmute yourself so that you can shout out and we can hear the question that you're trying to ask. Any comments, questions before we begin? Okay, well then let's move into the first lecture, which will be David giving us an introduction to take us from the kindergarten class to the master class level of bioenergetics. David.
Okay, right, switch to me. Hello, hello. So let me share my screen. O'clock in the evening, and my lovely wife has promised me a bite of dinner when I finish this lecture. Those of you who are in Hawaii, I think it's very early in the morning, and our Antipodean colleagues, it's the middle of the night. So if your eyes sort of close during the session, I will understand it and be appreciative. Okay. The theme of virtually everything we're going to talk about is the proton circuit. And we're going to be talking about the voltage and the current in the proton circuit. And as will very soon become clear, everything is based around an electrical analogy of volts and amps. So let's begin by going back some almost 50 years to Peter Mitchell and the original papers on the chemiosmotic hypothesis. And it might seem today, in the light of hindsight, that this was so perfectly obvious that people immediately leapt upon it. But the reality was actually very different. His original proposal in 1961 was extremely puzzling and controversial. And even 5 years later, when he produced this book, it was called The Little Grey Book, by analogy to Mao Zedong's Little Red Books at that time. It's worth reading, actually. It was reprinted in BBA almost 10 years ago for the 40th anniversary. And Mitchell was really before his time, because it was before we had any structures of the respiratory chain complexes, or particularly ATP synthase. So everything was based on a rather sort of mechanical system where protons were released from NADH, for example, being transferred to a iron sulfur center, protons being released, and a very sort of mechanical idea, which now, of course, has been totally superseded by the idea of conformational coupling and very complex proton pumps. He had absolutely nobody had any structure associated with the ATP synthase. And so this very sort of classical, again, chemical idea of the ATP synthase was proposed, and this was, what, 20, 25 years before the wonderful crystal structures of this proton-driven turbine, which was our modern concept of the ATP synthase. So on both of those aspects, he was before his time. The actual structures were not sufficient to give a true mechanism. But what was remarkable was that his figure 14, he said, how could these systems, however they work, the electron transport chain, which he called the oxidoreduction system, the ATP synthase, which he called the hydro-dehydro system, and everything linked, this was a proton circuit. And this complex of the proton circuit, which is what I've been working on for the last 40 years or so, if you just change the nomenclature to be more up to date, electron transport chain, ATP synthase, and so on, this still remains 100% valid after 45 years, which is quite remarkable. So his mechanisms of proton pumping have been totally superseded. His mechanisms of the proton circuit remain absolutely valid to date. And this is largely what we're going to be talking about over the next 3 days. So let's start very basically, because we're soon going to get much more complicated, with the entry of acetyl groups into the citric acid cycle. And as you're aware, the carbon dioxide is released in 2 decarboxylase stages, and the electrons are harvested through NADH at 3 sites and FADH2 at a 4th site. And these electrons then enter, this is NADH entering the electron transport chain. These are 2-dimensional shadow pictures of what we believe the structure to be like now. The electrons enter through complex 1, produce ubiquinone to ubiquinol, which goes to complex 3. Complex 3 transfers electrons via cytochrome C to the final complex, complex 4, cytochrome C oxidase, and those electrons are used to reduce oxygen to water. 4 electrons reduce 1 oxygen molecule to 2 water molecules. And this you'll all be familiar with as the basis. And then when it was possible to investigate the redox chemistry of the complexes, and in particular to measure the redox potentials, which we'll deal with in a couple of hours, of the different components, it becomes clear that electrons are feeding in from NADH at a potential, again to be defined in an hour's time, of minus 300 millivolts, and are leaving at a low potential of plus 800 millivolts. And the sign confusion, of course, goes back to Benjamin Franklin rubbing a cat with a bit of amber and saying that's positive and negative electricity, and basically getting it wrong, so electrons are negative. And that's why we've got to have this confusion throughout, that negative potentials are high, and positive potentials are low energetically. And so what the chemiosmotic theory, as it develops, has revealed is that these three complexes, 1, 3, and 4, are redox-driven proton pumps. And we now have a pretty good idea of their stoichiometries. I maybe explain later this curiosity that 6 protons enter and 4 protons leave, 2 protons enter and 4 protons leave. It's that the two missing protons have gone on to UQ to make UQH2. And so this is basically the stoichiometry of the electron transport chain. 4 protons enter complex 4, 2 protons leave because the other 2 protons are used to make water down here. So this is a basic energetic model of the coupling between the loss, the voltage drop of electrons being conserved in proton pumping by the electron transport chain. And if we put this together, we have the beginnings of a proton circuit, and the proton circuit is going to be absolutely central to all our lectures in the next 3 days or so. And here we have complexes 1, 3, and 4, each pumping protons across the membrane. And again, with an electrical analogy, the important thing is that with respect to electron transport, these 3 complexes work in series. They work one after the other. With respect to proton pumping, they work in parallel. And in parallel means that the proton current generated by the 3 complexes are basically added together. So the proton current is the sum of the currents through each of them. The voltage across the membrane is the same through complex 1, complex 3, and complex 4. So in series with respect to electron flow, in parallel with respect to electron pumping. Now, electrons from succinate and various other substrates, alpha-glycerophosphate, are part of fatty acid oxidation, don't have enough energy to feed into complex 1. They bypass complex 1 and they feed in at the level of ubiquinone. So there's no proton pump involved at this stage. They reduced ubiquinone to ubiquinol, and one just uses the last 2 complexes, complex 3 and complex 4, for proton pumping. So the stoichiometry, the number of protons per electron, are different for succinate and related substrates than for substrates that feed in through complex 1 via NADH. And then we put the whole thing together at the top. We have a complete proton circuit. A circuit has to be completed, and the protons that are pumped out by complex 1, complex 3, and complex 4, largely but not entirely, go back through the ATP synthase, this wonderful proton-driven turbine, to produce ATP. If we just think a little bit about the ATP synthase, if it was left on its own, it would, and just alone in the membrane, it would be an ATP hydrolyzing proton pump. It would pump protons out of the mitochondrion and hydrolyze ATP. But the fact is that its 3 brothers, complex 1, complex 3, and complex 4, are, if you like, more powerful. They generate a higher voltage, a higher proton motive force, and this forces the ATP hydrolyzing complex to run backwards as an ATP synthase. So this is being forced to run in the opposite direction it wants to go. Protons are forced back in, and ADP is phosphorylated to ATP, whereas if this was working in isolation in the membrane, it would be the other way around. So the 3 upstream pumps are forcing the 4th pump to go backwards. And at the bottom, we have my favorite model, which is a simple electrical circuit. And this isn't just because this is Bioenergetics 101. This is what we have in our minds throughout, at least I do, when I'm studying the complexities of the proton circuit and bioenergetics. Imagine you've got 3 Duracell batteries, which we can call battery 1, battery 3, and battery 4. These each generate about the same voltage. It's not as much as a real battery. They generate about 200 millivolts. And they contribute to a circuit. And the circuit is completed by two components. One goes through this light bulb, and this light bulb represents the complexity of the ATP synthase. And some of the electrons leak back across the membrane, and we're going to be dealing a lot with this leak. And that leak is shown here, and it's shown as a resistance, if you like, a resistance across the membrane. So put this electrical circuit central in your mind, and you will be able to follow more or less everything, assuming you remember what a volt and an amp is, to follow virtually everything that we've been talking, or we'll be talking about for the next 2 or 3 days. Here's the succinate circuit, if you like, which is the same, except we're not using the first battery, we're just using the second and third batteries. So the current is just generated by 2 batteries. The voltage is essentially the same as it would be if the third battery was there. There's our light bulb, there's our resistance. Now, let's start playing with the proton circuit and the electrical circuit analogy. And two of the synthetic agents you're going to be exposed to continuously for the next three days or so, and which you'll be very familiar with if you have any use for the seahorse respirometer. The first is oligomycin. Oligomycin inhibits the ATP synthase and stops protons flowing in either direction through the ATP synthase and blocks ATP synthesis. So if we are thinking in terms of our electrical analogy, what we're doing is that we've opened this switch and switched off the battery. So the battery switched off the light bulb. The light bulb has gone dark, and the only current in the electrical circuit is through this resistance. Similarly, the only proton current is through the leak pathway, and the leak pathway is I'm going to discuss in a few minutes. And so essentially what you would see in an electrical circuit, you would see a drop in current when you opened this switch. And you will also be interested, you see a slight rise in voltage. You remember any electrical circuit, the more current you draw, the voltage drops slightly. If you try to start your car in these northern climes in the middle of winter, then with the lights on, the lights go dim as you press the starter, because the heavy current that the starter motor is drawing causes a considerable drop in voltage. And in fact, this slight drop in voltage is very informative. We can study it with our voltmeters, which we're going to be talking about later. So now all the proton current is going through this endogenous leak. We can vary the leak and we can increase it. And the classical way of increasing the leak, which will be familiar to, I hope, all of you, is to add a protonophore, a proton translocating ionophore. And the standard one we use at the moment is called FCCP, and I'll talk a bit about FCCP later on. If you add a lot of FCCP, it's like putting a thick bit of copper wire across the terminals of the battery, and the voltage drops and can drop dramatically towards 0 if you put in too much FCCP. The current increases, until it becomes limited by the capacity of the 3 batteries to churn out electrons in that case, or to churn out protons in this case. Now, there are 2 rather curious variations of the proton circuit, which we can do artificially. One is to feed the electrons into succinate instead of to NADH, so we give succinate to the substrate. And succinate feeds its electrons through complex 3 and complex 4. And interestingly, these 2 complexes are slightly more powerful than complex 1. They generate a slightly higher voltage than complex 1. So they force complex 1 to run backwards. Just as we saw earlier, we talked about the ATP synthase running backwards. And what this means is that electrons from succinate reduce ubiquinone to ubiquinol, and some of those ubiquinols feed the electrons back into complex 1 by a process which we call reversed electron transport. And that reversed electron transport produces NADH. So this apparently energetically impossible thing that less energetic electrons from succinate to fumarate can reduce the much more energetically demanding NADH to NAD is possible because the electrons going downstream are generating a high voltage, a high proton motive force, but through complex 3 and complex 4. We can do this in a slightly different way by totally blocking electron transport through complex 3 with this inhibitor antimycin A, and then adding ATP under conditions where the ATP runs backwards, as I talked, and becomes a proton expelling proton pump. ATP is hydrolyzed to ADP and phosphate. Protons are extruded through the ATP synthase, and those protons can again drive complex 1 backwards. So we can see from succinate, now the only way, so succinate feeds electrons into ubiquinol, they can't go downstream, we block that, but some of them go upstream by, again, reversed electron transport to reduce NAD to NADH. Everybody happy at this stage? ATP reducing NADH. So we're going to have a series of take-home points in all my lectures. And the first take-home point, and if this is the only thing you get out of this lecture, then you've earned your $100 fee, basically. Think of the proton circuit in electrical terms of voltage, current, and conductance. Think of it not as sort of strange blobs of protein embedded in a membrane. Think of it in this very physical terms of voltage, current, and conductance. Now here's the proton circuit again. I've made it more complicated because what I've put in are some of the additional things that the proton circuit drives. We tend, I think Martin and I both tend to use a rather dangerous shorthand to think that the proton leak is simply a single homogeneous process. In fact, it's quite complicated. We'll be talking later about specific proteins, uncoupling proteins, which are designed to give physiologically regulated proton leaks. But the proton circuit can drive calcium cycling across the inner mitochondrial membrane. In most cells, most mitochondria, proton entry exchanges for sodium, sodium entry exchange for calcium, and calcium cycles around the membrane under steady state conditions using a little bit of the proton circuit. If we go over to the left, we find that some of the proton current is used to drive the energy-linked transhydrogenase, which transfers electrons from NADH to NADP, and is one of the reasons why the NAD pool is much more reduced than the NAD pool in the matrix of mitochondria. Again, some of the proton circuit is used to drive the uptake of phosphate and the uptake of other substrates into the cytosol. So when we talk about proton leak rigidly, we're talking about a conglomerate of these different processes here. So that's, and all of those that I've occasionally talked about in the beginning were perfectly described by Mitchell in 1966. And so basically this is just a rehash of his original typewritten diagram in 1966. We can go one stage more complicated into the intact cell. I spent many years working on neurons, and in neurons we have to deal with a complexity of ion transport processes across the plasma membrane. Sodium pumps, calcium pumps, potassium channels, sodium channels, calcium channels, a whole sort of gamish. And yet we can still use this basic idea of volts and amps in an intact cell because, go back, we can still measure the oxygen uptake in terms of the proton current, and we can still measure the voltage across the membrane, although it's considered more complicated measuring the voltage across two membranes at the same time. And I'm going to deal a whole problem-solving session in order to deal with that. But essentially, the proton circuit is sitting at the center of this vast, complicated transfer of ions across both membranes, and we can still use it and get useful information out of this. in a real complicated cell. Second take-home point, therefore, is that the proton circuit idea is not just for isolated mitochondria. It works equally well with some limitations in the intact cell, in intact cultured cells. Now, I want to talk a little generally about current and voltage in the context of the mitochondrion. And any energy flow system has two components, which we can call extensive and intensive. And we start with the example of a couple of waterfalls in South America. This is the Angel Fall, which has enormous height and rather limited water flow. And these are the Iguazu Falls in northern Brazil, which have an enormous flow of water and also quite a considerable height as well. And if you were to commit ecological vandalism and tap all these waterfalls to produce hydroelectric power, then the power you will get out is a product of the water flow over the waterfall and the height of the waterfall, and the power is height times flow. Height is intensive, flow is extensive. Now we can extend this now into the classical electrical circuit. For the extensive parameter, it's the amp.
I interrupt, David, for two reasons. One is to kind of set the precedent that it's okay to interrupt, but the other is just to point out that the definition. So extensive means it depends on the extent of the system. So if you have 4 waterfalls, then you get 4 times the water flow. So water flow is an extensive variable, but the height doesn't change. If you have 4 waterfalls, the intensive variable doesn't alter. It's always the same height. And that's one of the reasons that's really important, is it affects how you normalize things. So if you run a seahorse and you measure a rate, does it matter how much stuff you have in the well or not? And if it's an extensive variable that you're measuring, like oxygen consumption rate, it matters hugely how much is in the well. Because if you put twice as much stuff in the well, you get twice the rate out in terms of picomoles of oxygen per minute. But if you're measuring the membrane potential, that's an intensive variable. And it doesn't make any difference how much stuff you have in the well. You're just measuring the potential, and it's 180 millivolts. And you can have 10,000 times more mitochondria there, it's still 180 millivolts. So it's really important to understand the difference between extensive and intensive. And extensive depends on the extent of the system. That's the easy way to remember it. Sorry, David.
Okay. Absolutely right. So electrical circuitry, we have amps for the extensive current, we have volts for the height, if you like, the voltage. When we go to the proton circuit, the proton current, not surprisingly, is the extensive parameter. The proton motive force, the voltage, is the intensive parameter. And this is going to be a course with a lot of practical details. And the oxygen electrode measures the proton current, measures the extent. And to estimate the membrane potential, or major component of the voltage, we use the distribution of charged ions. And so virtually everything the three of us are going to be talking about for the next 2.5 days or so are going to be talking about proton current or voltage, proton motive force. So we're going to start just briefly by discussing the ammeter. And if you start to think about it, the idea of being able to measure the proton current, the microscopic proton current flowing across the individual inner membranes of tiny mitochondria would seem absolutely impossible. And how do you measure it? As soon as a proton comes out, another proton goes back in again. And how can you possibly capture this? And the reason that it's extremely simple is that there is a precise stoichiometry in each of these complexes between the passage of electrons and the pumping of protons. There is very little evidence for any slippage in any of these complexes. So we can assume a precise fixed stoichiometry that if we measure the rate of electron transport down to reduce oxygen to water, and we do that by measuring the rate of disappearance of oxygen, and we normalize it for the stoichiometry, we are measuring the total proton current of all the mitochondria, all the cells in that incubation. And our current idea, our present idea, is that 10 protons are pumped across the inner membrane for every 2 electrons passing down to reduce half an oxygen to water. And so if we measure the respiratory rate, nanomoles of, we normally use this O, which is half an O2, it's just historical. Then the proton current in nanomoles of protons per minute is 10 times the respiration in nanomoles of O per minute for an NAD-linked substrate. If you're dealing with succinate, the number comes down to 6. But it means that oxygen measuring devices, oxygen electrodes, are ammeters. Third take-home point, the oxygen electrode is the ammeter of this proton circuit. It measures the current. And if we think about this in a bit more detail, if your supervisor is well funded, she might have raised the $200,000 to buy an outrageously expensive seahorse. And she spent a fortune to measure something that just does one thing. It measures the rate of reduction of oxygen by complex 4, just a single enzymic process out of the thousands in the mitochondria in the cell. So it's a lot of money for something that does just one thing, the activity of complex 4. So why is it so versatile? And the versatility comes from the fact that one can design an experiment such that the factor which has the biggest control over electron transport is the thing you're interested in. And this is a sort of the key feature of everything we're going to be talking about in terms of the seahorse, for example. You can design experiments where metabolite transport is controlling the rate. You can measure the activity of a substrate dehydrogenase by making that having the largest control over the rate, respiratory chain complexes, adenucleotide translocator, the ATP synthase itself, how big is the proton leak, how much spare capacity do you have in order to produce a bigger current if you need to. All of these things you can get from a simple measure of the activity of complex 4 by making whatever you're interested in here, as far as possible, controlling the overall rate of electron transport and therefore oxygen uptake. And it's the design of experiments to do this, which will be central to our problem-solving sessions in the next few days. So here's the important conclusion. You've got to design an experiment so that what you're interested in must show as much rate control as possible. And this means, of course, decreasing the rate control by the other steps that you're not interested in. And this will become apparent when Martin starts talking about mitochondria, when I start talking about intact cells. Okay, four take-home points. This will be amazing. You're getting 4 points out of a single lecture. This is a very good use of money. The fourth one, to investigate a step with an oxygen electrode, you remove the rate limitations from all the other steps as far as is possible. Now the voltmeter. Yep.
I just want to bring attention to a question someone else posed in the chat.
Yep. What was the question?
David, I can read it. Proton current being 10 times the electron current is dependent on the cell respiring exclusively by oxidizing NADH. In a living cell, is this mostly true? Question mark.
Yeah,
Question
these
is easy to answer.
yeah. So these are situations with clean substrates. So with an NADH link substrate, purely it would be 10. With a pure Q-link substrate like succinate, it would be 6. In reality, it's more complicated. So the absolute number is not going to be as precise as we're talking about. As long as the substrate supply, it's a bit disturbing. As long as the substrate supply doesn't vary particularly, then the number will be the same. So the relative changes will be there, even if the absolute value is different. So that is correct. We're talking ideally here for a pure substrate delivery. With fatty acid oxidation, for example, the beta oxidation down to acetyl-CoA is 50% through NAD, 50% through Q, and so the ratio would be 8, halfway between 10 and 6. So that's a valid point. Is that okay?
When Shona goes through some of the glycolysis ox-phos balances in cells, that question becomes very pertinent because it's one of the numbers you have to stick into the equations to interpret what's going on. So she and I have spent a lot of time thinking about this question and both trying to regular conditions in cells so that it's actually true, and you can do that. If you give a cell only glucose and you starve it of anything else, then it's more or less true that all they run is the appropriate ratio of NADH from the Krebs cycle and 2 electron transport from succinate dehydrogenase. But in a real cell, under real plasma conditions, obviously it's got a whole mix of things it's using, and some of the electrons are coming in through complex 1, some are coming in through complex 2, some are coming in through glycerol phosphate dehydrogenase, some are coming in through the ETF system from a whole range of things, including fatty acids. So in real life, it's much more complicated than this simple conceptual model that we all use when we're trying to understand the underlying plumbing of the system. And Daniel, do you not have the ability to unmute and ask a question?
No, I did. I just raised my hand. I didn't want to interrupt.
Oh, you should interrupt. So
No,
just everybody else,
interrupt.
please interrupt. So Daniel should have said, "Stop, David, stop, stop, I've got this question." And then we could have all listened to that.
Okay.
So Zimple had a question. Do you want to ask it? Do you want to unmute and ask your question?
I have a question.
Richard.
So are we assuming these are functional mitochondria as opposed to mitochondria, dysfunctional mitochondria from a diseased organism?
I think the strength of what we can do is we can assess the degree of dysfunction. And so it's very limited interest if all we do is to study perfect liver mitochondria. The important thing is that we can measure differences in photon leak, differences in phosphorylating capacity, electron transport chain deficiencies. All of that is available. So I gave a sort of list of things that you could actually measure, dehydrogenases, transport, and so on. If you design the experiment carefully enough, you should be able to detect at what stage the deficiency is. So it's analytically extremely powerful. Otherwise, it just becomes of very limited interest. If it only works as an academic exercise, here is a rat liver mitochondrion, measure what we've measured for the last 40 years.
I understand that. I was just...
No, it's a good point. Okay, any other questions?
Yeah, there was a question from Zimple or Zimple, I don't know how to pronounce it. We can't hear you. No. Okay, while you fix that, let me read out her question.
Yeah.
Do electrons always move in one direction towards complexes 3 and 4? And why, unless blocked with antimycin A?
Complexes 1 and 3 operate close to equilibrium. So in other words, the energy they get out of the electron transfer and the energy they put in to the proton gradient are rather closely balanced. They can come rather close to equilibrium. And I've already given you one example, which is that complex 1 can run backwards. That's reversed electron transfer. Complex 3 is also close to equilibrium, and I'm just trying to think of the conditions. These are artificial conditions where complex 3 can run backwards as well. The only one which is irreversible is complex 4. Nobody has really succeeded in reversing complex 4. So that's the irreversible step. The other steps are reversible. One could, for example, reduce the level of cytochrome C and get electrons flowing back through complex 3 if you trap them, for example, by oxidizing ubiquinol to ubiquinone. So it's near equilibrium bidirectionally in principle, apart from the final complex 4, which is irreversible.
Hydraulic analogies are always good. So if you think of it as rivers and waterfalls, the whole process is going to go downhill eventually. But between two sets of rapids, it's more or less flat water, and you wouldn't have to do very much in terms of pouring buckets of water in at one end of that flat piece of water to make the flow go in the other direction. So it's not easy to do it, but it can be done. I mean, maybe buckets of water is a bit silly, but if you had a big water wheel there, you could actually make the water flow go the other way in that flat bit of water for a while. But in the end, thermodynamics is going to win and everything's going to go downhill.
Okay, any more questions? We're well ahead of time. We have plenty of time for more questions.
Gavin has a question. Gavin, you can go ahead and unmute.
Hi, I'm Gavin. My question was, is reverse electron flow through complex 1 possible under conditions with NADH producing substrates entering complex 1, or does it happen in non-physiological conditions providing only succinate as a substrate?
Okay, this is fun because Martin and I have debated this for probably about 25 years, this business of what we mean by reversed electron transfer. So again, we have let's stick to hydraulic analogies here. So the origins of the reversed electron transfer came from experiments done by Lars Ernster in probably the 1950s or 1960s with submitochondrial particles. Submitochondrial particles are produced by sonicating mitochondria. The inner membrane turns inside out and they reseal. And therefore, for example, the NADH binding site is now on the outside. The complex 1 binding site is on the outside. Succinate dehydrogenase, again, the binding site is on the outside. Now, they were stuck in the fog of the chemical coupling hypothesis. They had no idea what was going on. But what Lasser observed was that under conditions you could feed succinate and reduce NAD to NADH. And he knew there had to be some sort of energy involved in transfer, but he didn't know what it was. So in that condition, electrons are flowing backwards. Now, the question is, and this is a philosophical point, I know Martin will have a slightly different take on this. My feeling, the observation is succinate oxidation produces a slightly higher proton motive force than NAD oxidation does. And it just means that, I mean, you have 3 totally different proton pumps. They bear no relationship to each other. It's amazing that evolution has ended up with 3 pumps that are almost totally matched in terms of power, in terms of voltage. They're very, very close to each other. Complex 3 and complex 4 are slightly more powerful. So, and you can tell this because if you are measuring the reduction of NAD to the reduction of NADH in an intact mitochondrion, and you feed that mitochondrion succinate, the NADH goes quite reduced. Yes, more reduced than it would be if you'd fed beta hydroxybutyrate straight into complex 1. So that means that the steady state reduction level of the NADH in complex 1 is higher in the presence of succinate. And Martin's emphasis is electrons flowing backwards. My emphasis with is that we've put a little dam between the 2 waterfalls, and therefore the water level has risen, still flowing forwards. But there's, because of complex 3 and complex 4, there is a bigger back pressure on complex 1 to push electrons forward, and the NAD tends to get more reduced. So my feeling is that generally where you've got both NAD and succinate working, NAD and ubiquinone link substrates both working, that the major effect is the raised proton motive force from complex 3 and complex 4. If you were just feeding through NADH, the moment complex 1 starts to reach equilibrium, you can't push any more electrons through complex 3 and complex 4. It's the same electrons, basically. So complex 1 becomes controlling for the maximum proton motive force. The current voltage relationship is controlled by complex 1. If you bypass complex 1 and feed the electrons into the Q pool, you have a slightly different current voltage relationship in that you have a slightly higher voltage. So my feeling is that the degree of reduction, the observation is that the degree of reduction of NADH increases if you feed electrons in additionally at Q as well as in complex 1. And I feel that is because of the increased back pressure from that proton motive force on the continued forward flow of electrons. But Martin, do you want to put a different take on that?
Generally, I would agree with that statement. As I was saying just before this, that the river always flows downhill in the end. So in the end, the flow is always from the NADH down to oxygen. But as David said, by putting obstacles in there, in this case, by having succinate pumping more protons and having a higher PMF, then you can push that equilibrium around complex 1 more to the NADH side. So in that sense, you are always getting some effect of the succinate, if not an actual reverse electron transfer. But this is a very topical question in the lab, and we're trying to understand it. So there are clearly pathological situations where reverse electron transport works. I'm sure Gavin knows that well enough. For example, during ischemia reperfusion in the heart, during the ischemia, you build up succinate, and then when you reperfuse, effectively the mitochondria in the heart are now like mitochondria in the test tube oxidizing succinate, and they run reverse electron transport for 10 or 20 seconds or a minute or two before all that succinate is used up, and then everything switches back to the more normal forward flow. But the question we're trying to wrestle with at the moment is whether or not there's reverse electron transport commonly in cells under more physiological conditions. And I think David nailed it correctly that formally there isn't. Electrons are not going backwards all of the time because the thermodynamics in the end says you can't do that. But you are getting poising of the NAD pool through the pressure of the PMF from complex 2. And that looks a lot like reverse electron transport. So a lot of the things connected with reverse electron transport in complex 1 do happen all the time. And when I talk about ROS production by complex 1, for example, I think that's what's going on physiologically, is that complex 1, under this condition of being poised by complex 2, is running the Q site and making superoxide much of the time. So that comment will, I hope, become clearer in lecture 5 or whatever it is, where I talk about ROS production.
Yeah, we agree.
Thank you.
Any other questions before I carry on?
Hi, Carl, here. I'm wondering, I don't expect the composition of the mitochondrial membrane to affect the membrane potential, but does it affect the flow or the movement of ubiquinol through the complexes and affecting respiration?
This is interesting because ubiquinol, the mitochondrial form of ubiquinol is UQ10, which means it has an enormous, is it 40 or 50 carbon hydrophobic chain attached to it. So it is locked in the middle of the membrane, able to transfer laterally. And I don't know of any circumstances where that really becomes limiting. I mean, essentially ubiquinone is the electron collector from complex 1, complex 2, electron transferring flavor protein, glycerophosphate dehydrogenase, and various other rather specialized dehydrogenases. So they all feed into this amorphous, very large pool of ubiquinol that appears to be freely mobile within the inner membrane and then delivers its electrons to complex 3. Now, for example, some of the most exciting work at a structural level in the last few years, continuing, is the attempt to understand how complex 1 works. And complex 1 is the most complex complex, and it's the most enigmatic complex. And apart from it, the most extraordinary thing is that the sites of proton pumping are enormously distant from the sites of electron transfer, which seems absolutely extraordinary. And the model, I mean, I'm not up to this year's model, but the model which Leo Sazonov has is a pipe, if you like, going into the hydrophobic, or going deep into complex 1, that an ubiquinone goes in, picks up 2 electrons and 2 protons, leaves, another one comes in, another one leaves, and this has to happen, you know, hundreds of times per second, which I find very difficult to understand. So that implies that the ubiquinol is, they're incredibly mobile within the inner membrane. So as long as your inner membrane is proton tight, I don't know of any experiments that show that you can alter the composition of the inner membrane and get some sort of kinetic restraint that the UQ10 can't move fast enough. Is that
could butt in. I mean, when we're talking about these theoretical models of OXPHOS, the membrane is entirely passive. It's simply something that protons don't cross at all or at all easily. And to a first approximation, that's true. So it works for these discussions at this level of how the chemismotic circuits all work. But the reality is that the membrane composition, particularly the fatty acid side chains, the disposition of different head groups, the cardiolipin and the pairing of different side chains in the cardiolipin, all of them affect the dielectric properties of the membrane. So just at a pure physical level, there are subtle effects of all of these things. And then as soon as you allow for biochemical interactions where different lipids are forming rings around different complexes and they're talking to each other, and the lipid rafts are forming or not forming, probably not very much in the mitochondria because there's not much space for them, then there's a lot of possibilities for much more subtle control of what's going on. But all of the experimental evidence says these things are not very quantitatively important for the underlying bioenergetics. So if they're important, they fine-tune some of the regulation maybe. And by and large, that story is not written yet. We really don't have a coherent description of how that might work. But I think we accept it can work at some level.
Just when Martin was talking about membranes there. Am I on? Yep. Then we talk about membrane potential, and this confuses some people because they imagine it's something to do with charge on the membrane. And at the level that we're talking, you could have a bit of plastic for the membrane, assuming everything else fitted into it without altering it. So membrane potential is shorthand for the difference in electrical potential between two compartments separated by a membrane. That's what we mean by membrane potential. It's nothing to do with the membrane. The membrane can be plastic. It's the difference in electrical potential between two compartments separated by that membrane. But that takes several lines to do it, so we just shorten it as membrane potential. But I know some people have this confusion that it's something to do with the charge on the membrane, that maybe the outside becomes positively charged, the inside becomes negatively charged, and that's not the case.
But nonetheless, that does happen. So if you look across the profile of a membrane, there are quite complicated charge distributions. So the phospholipid head groups, the phosphor part of the phospholipid is negatively charged, and that attracts cations, calcium, potassium. So you get sandwiches of negative and positive, and you get a really quite complicated profile of charge. And there's been a lot of discussion going back into the 70s and 80s about whether that affects the proton circuitry. So are protons being channeled along parts of that? Are they skating along the surface of the membrane? And by and large, that's fallen by the wayside because people haven't found convincing evidence that it's true. Mostly the mathematical models are still valid, so it might be true, but no one's ever really demonstrated an occasion where it matters. So we've lost interest in it rather than it's not happening. So again, we're oversimplifying as a piece of plastic, two bulk phases, talking only through proteins plugged through the membrane. It's really more complicated than that. But the beauty of it is that we can describe it ignoring all that complexity, and the descriptions work quantitatively really well. So it's a bit like Einsteinian and Newtonian physics. Our Newtonian description works. So why bring in relativity for most of the things we care about? But just now and again, relativity is essential to understand what's going on. And we haven't got that level of sophistication, mostly in the bioenergetics, to need the equivalent of relativity to explain what's going on. But it's happening, I'm sure.
Question. So, hi.
Yeah.
I like this, the analogy. So my sort of bioenergetically speaking, so you've got 3 batteries there. So I mean, I understand if you have 2 batteries, then if the batteries don't work over a long time, there'd be a problem. But bioenergetically speaking, if there were only 2 batteries there, so let's say complex 1 is not working, then the light, the current, everything should be the same. What can you discuss what would happen if there are just 2 batteries working at a time? What would be the consequences of that?
You can do this with isolated mitochondria, as I said, just by giving succinate. And there is no problem. Mitochondria are perfectly happy with succinate. The voltage, if anything, the voltage is a bit higher than it would be with all 3 complexes. You find that interestingly, that the proton leak, which is very dependent on the voltage, the proton leak goes up a bit higher than it would. You have to alter your multiplier from 10 to 6 to work out proton current in response to respiration. In a real situation, you would be in deep doo-doo for any considerable time. Because,
if you could change the batteries, then you would also be in, you would have a problem, or it's only that the batteries stop working and you need to replenish them all.
Maybe I can say something. So I think there's 2 ways to think about the problem. One is mechanical. So if you just get rid of complex 1,
right?
Does everything work? Yes, everything works. But ecologically, that's a problem because you have about a volt of available redox energy, and you're only starting at about 0. So you run about 0.7, 0.8 of a volt of it, and the rest you don't use. So it's inefficient. So if you're an animal out there competing against other animals and you only have 2 batteries, you would have to catch more prey or eat more grass in order to keep up with the rest of them. So ecologically, it's inefficient.
Right.
And then more interestingly, the other way of looking at it is, okay, but why don't you just have 2 pumps that cut the span in half instead of having 3 pumps that cut it in half? And that's all a matter of gearing and matching up all the different interrelated components of this system. And in the end, the thermodynamics drives it. So if you only had 2 pumps, you would have to drive your ATP-ADP ratio higher. And that would give you kinetic problems of ADP not being enough. And David will address some of these questions in a while. So the whole system is carefully designed with all the parts integrating thermodynamically with all the other parts. And if you go messing with that, you're in deep doo-doo, which is how David described it, because things don't match up and you end up having insufficient of something, or the potential of something is too big, or the leak reactions get bigger, and everything just doesn't work as well. So, I mean, I know it's a reductionist argument that biology did it, so it must be perfect. And we can't think of any way of improving on it. But this is one of those situations where it's really cleverly designed or evolved so that
Evolved,
it
please, not designed.
captures all of the energy, or a large amount of the energy, in as efficient a way as possible, with a minimum of leaks and side reactions.
Sorry, thank you. Another thing with an intact cell, of course, is that your succinate comes from upstream NAD-linked dehydrogenases. You cannot run a cell on succinate alone because your succinate is coming from NAD-linked dehydrogenases. Thank you.
And a corollary to that would be there is a lot of interest in having NADH oxidases and alternative oxidases as cures or treatments of bioenergetic problems. So you could engineer to have an NADH oxidase from yeast or somewhere put into mammalian mitochondria, and you would have the situation you described. So you just take the NADH, run the electron state Q without any proton pumping, and then plug them into the proton pumping machinery. And that clearly has the advantage of avoiding inhibition of complex 1, but it gets you in doo-doo in terms of all these other things that go on. In terms of efficiency, you become inefficient. Probably you spill more electrons onto ROS at complex 3 because you're running your Q pool too reduced. So things go wrong when you do those manipulations. So they'll save you if you haven't got a complex 1, but you and I wouldn't want to do it because we do have a complex 1, and that's a really good system. You don't want to mess with it.
Oh, and in regards to the oxygen consumption, let's say you're running this, would that could be lowered if you ran 2 batteries, or if you ran reduce the current, right? They're two, both different ways could lead to a reduction in the oxygen consumption.
Yeah, but then you go to less ATP with time, and you need it in order to do things.
Right.
So basically you have a black box. The energy is what goes in with respect to what goes out and how fast it is. So you cannot get out more energy than you put in, basically. So
well,
reduce,
Right, I was more thinking, and we can discuss this in a few other lectures, but so yes, say you want to turn down the amount of ATP. Let's say you don't need as much ATP. What is a more efficient way? What is an efficient way to do it? Use 2 batteries or turn down the current? And so maybe we can answer later. Or
if you need less ATP, then you automatically shut down the proton current. It's self-regulating, the respiratory control.
Equally.
The proton current is. Are you still seeing my slide up here? So that the proton current is defined by the re-entry. Let's forget about the leak. Re-entry through the ATPase. If you need less ATP, this decreases, and so the proton current decreases. It's so you're decreasing the current through the battery. You're putting resistance in here or through the light bulb, and the whole proton current will reduce. So it's a beautifully self-regulating system that the respiratory control says, apart from this leak business over here, that your electron flow is always the absolute minimum needed to produce the amount of ATP that you need. You alter the amount of,
Crucially important concept that comes up later in the ATP calculation lecture as well. So so I would describe it in terms of ATP production as you make exactly as much ATP as is needed to meet ATP demand in a cell most of the time. Of course, that's not always entirely true, but generally speaking, you don't make extra ATP.
And then the interesting overlay is, and this is not proved, but is an intriguing concept, is that it may be that if you have too many mitochondria sitting there idling, not being used to make ATP, then of course you do two bad things. One is you leak protons, so you're just leaking energy, so you're idling but wasting a bit of energy, and ecologically that's probably a bad thing. And also you're running at high potential, so you're probably making ROS, which is probably not a good thing. So it looks like nature has also evolved ways to shut off whole swathes of mitochondria by sealing up the outer membrane. So you just seal them off so that they can't talk to the cell, and then they drop out of the bioenergetic protocol until you need them, and then you bring them back in. So that's an idea that's being pushed particularly by John Lemaster's group. I like it. It's not well demonstrated, but it would be an example of what Pankaj is talking about. You can take your mitochondria offline and bring them back online when you need them. And that's overlaid on the dynamic regulation that Shona and David are talking about.
Okay, shall we continue?
Yeah.
I have a quick question related to what we are talking. So when we talk about the complex one, from my understanding from the earlier points, that the complex 3 and complex 4 are more efficient than complex 1.
No, not efficient. There's no difference in efficiency. 3 and 4 generate a slightly higher voltage. It's nothing to do with efficiency. The complex 1 and complex 3 are highly efficient in that the energy you get out is very close to the energy you put in. Complex 4 is not. It's the final waterfall. And because it goes to completion in one direction, it is less efficient because it's not reversible, or it's not reversible because it's less efficient. But there's no difference in efficiency between complex 1 and complex 3. I mean, these are totally different things. They've come from opposite ends of the biosphere, and yet they talk to each other and integrate into a membrane and give electrons to each other. It's amazing if it works at all.
Right. So if there is a condition somewhere in a cell, if there is a metabolite that can actually kill the complex 1, or it can actually stop any flow into complex 1, then there will be more leak. There will be more leak cycle, right? So because if
you've got a real cell and you block complex 1, respiration fails. The cell dies basically, or it can't respire. You can't bypass complex 1 unless you've got a continual supply of stuff that feeds into complex 3. And in a real cell, you don't have that continuous supply because the succinate comes from NAD-linked dehydrogenases in the citric acid cycle.
So there cannot be a condition where complex 1 is completely blocked.
Well, it can be, but you might find yourself doing some practical problems which look at the effects of blocking complex 1 in the next day or two.
Okay, thank you.
Right, let me proceed because my dinner is waiting.
David?
Yep.
Hear me, it's Ricky. You have 10 minutes.
I'm sorry?
You have 10 minutes.
I know, yeah.
Okay.
I'm watching the clock very closely, but my wife has got a nice food ready for me in 10 minutes, so I will have to disappear and eat it before I return sharply for the rest of the evening. Proton motive force is membrane potential plus a component of the pH gradient. We're going to devise the mathematics of it later this evening, but the equation is that proton motive force in millivolts is the membrane potential. Remember, that's the difference in voltage across the membrane, minus 61 times the delta pH. The minus sign is another case of mixing up positives and negative. Mitchell defined a positive delta pH as one that is acidic in the matrix. Normally across the gradient is the other way around, and so we have to subtract this Mitchell-defined delta pH in order to add on to the proton motive force. A delta pH of -1, if there was a pH 8 inside and 7 outside, would contribute 61 millivolts to the proton motive force. So remember this negative sign is just because, just like electrons, we got the delta pH sign convention wrong. Typically in a mitochondrion, about proton motive force is of the region of 180 millivolts, of which 150 millivolts is membrane potential and half a pH unit, in other words, 30 millivolts, is pH gradient. This is very variable, but this is a typical value that we can actually work with. Monitoring membrane potentials is going to be tomorrow's practical. Wednesday's practical. We use lipophilic cations. We believe that cations can't cross through lipid bilayer membranes, but there's a special class that can. This is a lack of an electron, a positive charge, and the alternating single and double bond structure over the entire hydrophobic molecule means that that electron lack, that hole, is delocalized over this large planar structure. It's called a pi orbital system. That decreases the charge density and makes it readily permeable across the membrane. It's also fluorescent. This is a cell body, and you can see the individual mitochondria. And the practical on Wednesday is going to deal with how we get not quantitative, but reliable qualitative details of membrane potential out from this complexity here. So next take-home point, we use the distribution of membrane permanent cations to estimate voltage, membrane potential, but membrane potential is not the same as proton motive force, because proton motive force has to include the pH, delta pH component. The approach which Martin has developed with isolated mitochondria is to largely eliminate the delta pH component, converting it into back into a higher membrane potential, and I'm sure he'll be talking about this a little later. So what's good about measuring respiration is that it can be quantitative, especially with isolated, well, it can identify small changes in pathways. You can make a lot of experiments rate controlling. The problem is it only works on cell populations and gives no information on processes that are not rate controlling. It can basically look at one process at a time. So you have to devise multiple conditions to look at multiple limiting events. Measuring voltage, especially if you've got a nice fluorescent microscope, you can work at single cell or single mitochondrial level. And what's very useful is you can link measuring voltage with different fluorophores, measuring calcium, plasma membrane potential, reactive oxygen species, etc. But at best, it's semi-quantitative. Our colleague Akash Gerentser has improved the quantitation of this considerably. Most people ignore delta pH changes. I'm guilty of this as well. Of course, it doesn't give any information on rates. And you have to bear in mind you've got a plasma membrane as well, and the changes can be relatively small. Whenever possible, if you've got the apparatus, measure both. Last point I want to cover is Ohm's law and conductance of these leak pathways. And conductance is current over voltage, just like resistance is voltage over current. So conductance is proton current divided by proton motive force. If you can measure both of them, you can measure the conductance of the leak pathways. And I'm going to be telling you about how this was done in one very specialist tissue, brown adipose tissue, with uncoupling protein 1. Another important feature, again based on this, is internal resistance. I told you that as you increase the current drawn by an electrical circuit, the voltage drops, albeit can be somewhat slight. The voltage drops as the current increases. This is a experiment with isolated mitochondria, rather sort of schematic experiments showing respiration in the limiting state in the absence of phosphorylation, which we call state 2 or state 4. This is where we give ADP and you get rapid respiration for state 3. The ADP runs out, you go back to state 4. And this is what you get if you measure the voltage. And this is the sort of drop you get going from state 4 to state 3. We're going from the slow respiration where you're not generating ATP to the rapid respiration when you are. It's a very limited drop in potential, just maybe 10 or 20% of the total proton motive force. if you add a lot of FCCP, a big excess of FCCP, a fat bit of copper wire, the potential can drop down close to 0. When we're dealing with the seahorse, the protonophore concentration is critical. This is starting in the absence of ATP synthesis, which is called state 4, slowly increasing ATP turnover or adding an uncoupler. Respiration increases until you reach the stage where the delivery of electrons becomes rate limiting, rate restricting, and then there's no further increase. And if you want to measure maximal respiration, you want to get to this point here. You don't want to add an excessive FCCP. If you drop the proton motive force further, then you get all sorts of problems with substrate transport into the mitochondria, etc., which you want to avoid. But this will become clear when we discuss the seahorse respirometry. Final point, how do protonophores work? They work on the same principle that the membrane permeant potential indicators, cations, work, in that they have a large pi orbital delocalized electron cloud such that the negative electron on FCCP minus is spread over the whole structure. So unusually, FCCP minus is permeable across the membrane, and the protonated FCCP-H is also permeable across the membrane, and the protonophore cycles, picks up a proton outside, crosses protonatedly, drops it inside, comes back as the ion, and cycles around continuously. And that's how protonophores work. So we're finishing exactly on time here. The electrical analogy is powerful and you can use it for everything. Basically, that's the take-home point. I've given you 6 take-home points, and I hope that will help the understanding in the future lectures. So now it's time to go into breakouts. I hope that Martin and Shona can do the bulk of this. I've got to eat my dinner and come back in within half an hour. I'll be gone about 15 minutes or so.
I'm going to put you all in breakout sessions.
Yeah.
I do want to quickly mention that they should be breaks. If you need a break, please take a break. This is very informal.
Yeah.
Problem with a coffee break that's not a break is that you can neither take care of yourself nor go get coffee. But yes, please feel free.
So I'm going to join my breakout room after I've made a cup of coffee. And what's going to happen now is you're all going to find yourselves in randomized breakout rooms. Take the opportunity to network with the people you find there, or take the opportunity to go to the bathroom or go and feed your dog or whatever else you need to do. But take that opportunity to network, and we'll all meet again. You'll be dragged back into the main room at what time? 10:30.
10:30.
So Ricky will bring us all together again at 10:30. So enjoy. See you at 10:30.
PowerPoint.
Yes.
Yeah.
Good. Okay, so this is going to be the hardest lecture and covering some of the most important points. And it's something which scares people to bits, basically. So I'm going to try and demythologize it. And I wrote the first edition of the bioenergetics book back in 1982. And in writing it, I realized I did not understand thermodynamics at all. And so the writing of the original chapter 3 was a voyage of discovery for me, trying to understand from first principles what the physical chemists were trying to say. So I hope I can answer some of the main questions that hover at the back of your mind, but you're scared to actually ask. Now, the first problem is that we all know that the driving force in the universe is an increase in entropy. And yet, when you read a textbook like mine or a physical chemistry textbook, it doesn't mention entropy. It mentions something rather strange called Gibbs free energy. So what is Gibbs free energy? Why do we use it rather than entropy? And more importantly, what is equilibrium thermodynamics? So this is the basic principle that a process can only occur if the entropy of the universe, by which I mean a system plus its surroundings, increases. That's the definition of a process which can occur. And then, rather confusingly, equilibrium thermodynamics deals with closed systems which can exchange energy but not material. And what on earth relevance does this have to cells and mitochondria, which exchange material as well as energy? That will come, of course, come to in a minute or two. And what Willard Gibbs derived in the mid-19th century was an equation or a function called the Gibbs energy change. And at constant temperature and pressure, which are conditions that apply to most biochemical and biological systems, a decreasing Gibbs energy change indicates an increase in the entropy of the universe. So in other words, if we use Gibbs free energy instead of entropy, we can just look at our system and ignore everything that happens outside the system and the rest of the universe. So if a test tube of mitochondria are producing heat, releasing heat, then we can ignore that and just look at what is happening in the actual test tube. We can ignore the rest of the universe, and it makes life an awful lot simpler. So, take-home point, Gibbs free energy changes, we use them instead of entropy because we do not have to consider what happens outside our system. Now I'm going to explain what we mean by our system. Problem is, as I've said, that living systems do exchange materials. So what Earth uses is equilibrium thermodynamics. What questions can we ask of equilibrium thermodynamics? We can ask, what are the equilibrium conditions for a process? When is a process at equilibrium? How far away from equilibrium is that process in the actual working cell? And as we're going to derive, the capacity to do work is a function of how far away from equilibrium you are. And these are two very important questions we can ask. The third question is the process energetically possible? It doesn't tell us if a reaction will occur, how fast a reaction will occur. What it will tell us is if a reaction is thermodynamically impossible. So thermodynamics is really a misnomer. It should really be thermostatics rather than thermodynamics. It doesn't tell us anything about rates, equilibrium thermodynamics. So what we've got so far is it tells us how far away from equilibrium a process is in the cell. It means that we do not have to consider changes in entropy out in the universe. It makes life a lot simpler. And the reason that we need to understand thermodynamics is that if we're dealing with the mitochondrial proton circuit and you try to read papers and try to understand papers, you will find three different manifestations of the thermodynamic processes. When we're dealing with electron transfer reactions or oxidation reduction reactions, we deal with redox potential change, reduction oxidation potential change, which we're going to define. When we talk about the proton circuit itself, we talk about proton motive force. Proton motive force is another manifestation of the Gibbs free energy change. Finally, when we talk about scalar reactions such as ATP synthesis from ADP and phosphate, we tend to use directly the Gibbs free energy change. So in bioenergetics, you come across Gibbs free energy changes, photon motive force, and redox potential changes. They are all basically the same thing. They're all basically Gibbs free energy changes. Take home point. Bioenergetics is the study of the processes into converting these three forms of potential: Gibbs free energy, redox potentials, redox changes, and ion gradients. Okay, everybody with me so far? So the definition is the process which results in a decrease in Gibbs free energy is one which causes a net increase in the entropy of the system plus the universe. And it may occur spontaneously if a mechanism is available. But sometimes a mechanism is not available. So a process can result in potentially a decrease in Gibbs free energy, but if there's no enzyme, the process will not occur. And we're going to talk, I've listed 4 here, but we're going to restrict ourselves to 3 types of Gibbs free energy change. And we're going to start by talking about biochemical reactions and focusing on ATP synthesis. Okay, something you're all familiar with. Capacity to do work is displacement from equilibrium. If you were to look inside a dead cell and measure ATP and ADP levels in the cytoplasm of a dead cell, in other words, at equilibrium, and you had a very sensitive way of measuring it, you would find that the ratio of ATP to ADP would be about 1 in a million. You might have 5 millimolar ADP and 5 nanomolar ATP. And that process is at equilibrium, has no capacity to do work. Imagine a spring which is at equilibrium. If we look inside a living cell, respiring cell, we might find that the ATP to ADP ratio, instead of being 1 to a million, is 1,000 to 1. Extraordinarily high value. You can actually look at this in respiring muscle, for example, and get this extraordinary ratio. And this is a highly compressed spring. The spring is a long way away from equilibrium and can do a lot of work. At equilibrium, you're at the bottom of the energy trough. You can't do anything else. When you're away from equilibrium, you can do useful work. Now, when we run this course live, this is where I ask my question. How many of you were taught in your undergraduate training that ATP is a high energy molecule? Can you put up your hands? There's one. Come on, I want to see pictures here of people. Yep, hands are going up all over the place. It's amazing. This is a total misconception, the idea that ATP is a high energy molecule. I'm going to tell you it's an extraordinarily low energy molecule. So your daily turnover of ATP is about your body weight, which in my case is about 90 kilograms. So every day you turn over about 90 kilograms, in my case, of ATP. Now, a real high energy compound is something like glucose. You can live on about half a kilogram, 500 grams of glucose a day. Your teeth are going to rot and you're going to get diabetes, but in terms of energy, that provides you with enough Gibbs free energy to keep you going through the day. ATP is not a high energy molecule. There's nothing magic about that bond there. If you have ATP and ADP at equilibrium in the dead cell, that ATP has no capacity to do work. It's at equilibrium. So energy is not stored in an imaginary high energy bond, but in the extent to which the reaction ATP hydrolysis reaction is displaced from equilibrium. And what I showed you underneath the strings in the previous slide was that in a working cell, it can be displaced at least 9 orders of magnitude, 10 to the 9th away from equilibrium, this reaction. And so all the energy that we're putting into the citric acid cycle, electron transport, the proton circuit, is in order to drive this reaction 9 orders of magnitude to the left away from equilibrium. A really quite amazing thing. I can repeat it because we need to repeat it. I only saw 4 or 5 people, and I think every hand went up. So I don't know out of all the 38 of you how many it was. Maybe we'll ask at the end. So it's not a high energy molecule. It's the ATP hydrolysis reaction, ATP to ATP and phosphate, how far that is away from equilibrium, which is the critical factor. Now, you're going to have to bite the bullet for the next minute or two because we're going to deal with some rather complicated and intransigent equations, and ones which confused me totally as an undergraduate and confused me until actually I rewrote the equations in the first edition of the bioenergetics book. So we're going to start.
Before we start the next part, can I ask a question about the equilibrium? Then in the cells, where do we place GDP, GTP in the same equilibrium?
It basically would obey exactly the same rules as ATP, ADP. So if the GTP, GDP pool was at thermodynamic equilibrium, the equilibrium constant for GTP going to GDP plus phosphate is almost the same as ATP going to ADP plus phosphate. If the GTP hydrolysis reaction was at equilibrium, you'd probably have a million times more GDP than GTP. So the processes which drive the GTPase equation or reaction away from equilibrium, I mean, I don't know all of them, but it's mainly coupled to ATP hydrolysis. There's for example, exactly the same thing occurs. So in other words,
but in terms of overall determining the rate of ATP synthesis, they compete for the same phosphate. And
yeah, but thermodynamics has nothing to do with rates. Thermodynamics is equilibrium thermodynamics. It's thermostatics. Okay, it's not dynamic. So it's very curious that we can use something that doesn't actually occur in vivo and get so much information out of it. So one must get away from the idea about talking about rates or competition. These things are at equilibrium. Is that okay?
Yes.
Right. Okay. We have time afterwards. I've eaten my dinner, so I have time to talk to people afterwards. Let's take a general equation. A molecules of A, B molecules of B, C of C, and D of D. And the hideous equation you see in physical chemistry textbooks, which turn everybody off, is this thing. Gibbs free energy is standard free energy plus 2.3 RT log to the base 10 of the observed mass action ratio, which means how much C you see, how much D you see, how much A and how much B you see when you actually observe the concentrations in a living cell. That's reported in the books, and I found it totally incomprehensible. And what I did, way ago, first of all, it involves this dreadful thing called standard free energy, which I'm going to totally demolish in the next 5 minutes, standard free energy. You get rid of it. And what I did in the first edition of bioenergetics was to simplify the equation as this very simple symmetrical equation. Gibbs free energy change is the same constant log to the base 10 of the equilibrium mass action ratio, which is this ratio at equilibrium, divided by the observed mass action ratio, which is this ratio that you actually see in the real cell. And it might surprise you, these are the same equation, but I've manipulated them to make it symmetrical and to make it obvious that Gibbs free energy is displacement from equilibrium. I'm not going to define this because I don't think I can remember how to define it, but we're going to take this as read, that this is the same equation as that. Gibbs free energy is a function of how far away from equilibrium you are. And delta G is capacity to work its displacement from equilibrium. Okay. 4 take-home points, and you've only been going for 15 minutes. That's pretty good. Now, I have several pet hates in biochemistry, but my worst pet hate is the so-called standard free energy. And standard free energies should be banned from all textbooks and from all biochemical and biological systems. Let's take our nice symmetrical equation. Delta G is this business times the log of the equilibrium constant over the mass action ratio. Now, there's a particular case which is called the standard state, when we put the observed mass action ratio equal to 1. 1 molar substrates, 1 molar products, 1 molar everything. And the question is, what is the Gibbs free energy in this standard state when, this is gamma, by the way, capital gamma, when gamma equals 1. When it 1, we just remove that bottom line, don't we? And so it becomes delta G naught is minus 2.3 RT log to the base 10 of the equilibrium constant. What does this tell you about standard Gibbs free energy? It tells you it's a logarithmic function of the equilibrium constant. It's another way of restating the equilibrium constant. It's nothing else. It's nothing to do with what happens inside a cell. I do this very large and I do it in red, and I'll probably show it twice because it's so important. So delta G is just a logarithmic version of an equilibrium constant. It tells you nothing about the real Gibbs free energy or whether a reaction can occur spontaneously. You go into any of the textbooks you've had as undergraduates. In my days, it was Stryer, Leninger, and so on. All of them spend most of their time talking about standard free energies when they're talking about glycolysis or whatever. And it is total nonsense. It's totally meaningless. It's just a logarithmic restatement of the equilibrium constant. I say it again. You can't claim I haven't sort of said this to you. You didn't understand it. It tells you nothing about whether a reaction can occur spontaneously. Now we're going to ask a question which you should be asking yourselves all the time when you're reading one of Martin's texts or my text, shown as whatever. And that is, we use this absurd equation. ADP goes to ADP plus phosphate, as though it's telling us something about the ATP hydrolysis reaction. But probably the real equation for ATP hydrolysis is that the ATP is complex to magnesium, combines with water, that goes to ADP complex with magnesium, which now has a negative charge, plus phosphate, probably the dianic form of phosphate plus a proton. That is probably the real reaction of ATP hydrolysis. And the equilibrium constant would be like this and totally unmeasurable, because we wouldn't be able to dissect out what exactly is the concentration of that, the concentration of that. It would be unmeasurable. It also has dimensions of molar to the squared, because it has 3 on the top and 1 on the bottom. So that's the absolute equilibrium constant. And the absolute observed mass action ratio would be just as complicated. That would now be capital gamma. And these would be the concentrations you measure in the cell rather than the equilibrium concentrations. The beauty of the symmetrical equation is that everything which occurs on the top and bottom that we don't measure, as long as the pHs are changed, that is the same. It cancels out on the top line for K, it cancels out on the bottom line for gamma. If your magnesium concentration is the same, it cancels out at the top of the equation, it cancels out at the bottom. And as long as we measure the equilibrium constant and the observed mass action ratio under identical conditions of everything you don't put into the equation: temperature, pH, magnesium. These all cancel out top and bottom. And water concentration, for example, I've even forgotten water, actually. There should have been water in the bottom. But they cancel out. And you can use this absurd equation, ATP equals ADP plus phosphate. All the other parameters cancel out. So it's actually meaningful. There's no error in this. But the limitation is that it's not an absolute Gibbs free energy. It's a Gibbs free energy under very specific conditions. So this is the apparent equilibrium constant for ATP hydrolysis under a variety of conditions where you're varying concentration of magnesium, the pH, and the apparent equilibrium constant changes enormously. It depends exactly where you are on this ski slope. So if you want to do an experiment under particular conditions, you measure ATP, ADP, and phosphate under those conditions, and you look up on a table what is the apparent equilibrium constant under exactly those conditions. Then you divide the one by the other, and that tells you how far or how close you are to equilibrium. So it's not a universal constant. You can use these apparent terms for the simplified equation only at a particular pH, magnesium concentration, etc. Everything you're not actually putting into this equation. So you have to look up on a table what is the apparent equilibrium constant for the exact conditions that you are measuring the mass action ratio. What is the pH, what is the magnesium, and so on. So it might be difficult to follow that. It's in the chapter 3, which I've given you, and which I suggested you read before, and you can sort of read through it and think through it. But it makes life possible because we can use this greatly simplified equation. If we do this, then here's our simplified symmetrical equation. Gibbs free energy, its capacity to do work, its displacement for equilibrium. If we take a few examples and we start off at equilibrium, where the mass action, we're doing this under specific conditions, pH 7, 10 millimolar magnesium, 10 millimolar phosphate. When we look up on the tables, the apparent equilibrium constant is 10 to the 5th molar. And when the ratio is 1, we're at equilibrium. The Gibbs free energy is 0. It's a low energy situation. The ratio is about 1 to a million. If we move to a ratio of 10 to the 5th, this means that the mass action ratio, the observed mass action ratio is 1. This is called the standard Gibbs free energy. The Gibbs free energy change is about minus 28 kilojoules per mole under these artificial standard free energy conditions. The ATP-ADP ratio is about 1 in 100. If we look inside the matrix of a respiring mitochondrion, we find we're about 10 to the 8th away from equilibrium, that we have an ATP-ADP ratio of about 10, which corresponds to a Gibbs free energy of about minus 46 kilojoules per mole. Amazingly, when we go out into the cytosol, we find that the ATP-ADP ratio is 100 times higher than it is in the matrix. I'll explain why in a minute. And this gives us a Gibbs free energy of almost minus 60 kilojoules per mole. Most of the energy for cytosolic ATP synthesis comes from the proton circuit and the ATP synthase. But the export of ATP and the uptake of ADP is driven by the membrane potential. The uptake of phosphate to make that ATP is driven by the pH gradient. Between them, you use an additional proton to export ATP from the matrix to the cytosol. And what you gain from that is an increase in Gibbs free energy and a cytosolic ratio of almost 1,000 to 1. So the adenine nucleotide translocator is driven by the membrane potential. Phosphate uptake is driven by the pH gradient. The sum is driven by the total proton motive force, And that means you can get 100 times higher ATP-ADP ratio in the cytosol than you can in the matrix where they're actually produced. Really surprising results, which fits with everything that we know. Okay, we have in 25 minutes covered Gibbs free energy of the most complicated system, which is the ATP hydrolysis reaction. It's not a, you know it's not a high energy molecule. You know its displacement from equilibrium. You know if you use the symmetrical equation, it's very simple. And as long as you know what the magnesium, pH, temperature, etc. conditions are. Phew, we're dealing with a lot, aren't we? We're going to move on to the second of our three conditions. We're going to talk about oxidoreduction reactions and redox potential changes. And before we start, these are also governed by the Gibbs free energies. They're an alternative way, historically different way of presenting Gibbs free energy changes. More confusion in the literature is you find people talking about hydrogen transfer, that NAD plus going to NADH is a hydrogen or a hydride transfer, that UQ going to UQH2 is a hydrogen transfer. That's absolute nonsense. Everything is actually an electron transfer. Everything involves electrons. Let's take three examples here. This is ferric cytochrome C. In the electron transport chain, ferric cytochrome C gains one electron and goes to ferrous cytochrome C. NAD plus, we know, goes to NADH. Think of it as a two-stage reaction. NAD plus undergoes a 2-electron reduction, making NAD minus, and NAD minus doesn't like being NAD minus, and it immediately picks up one photon to make NADH. NAD plus 2 electrons plus 1 photon makes NADH. Ubiquinone, 2-electron reduction followed by addition of 2 protons. UQ plus 2 electrons goes to UQ2 minus, and some very rapid reactions, for example in photosynthesis, can actually detect this UQ2 minus form before it picks up 2 protons to make the neutral ubiquinol UQH2. Don't refer to these as hydride or hydrogen transfers. They are electron transfers and the proton follows. Now, we're not just dealing with the electron transport chain here. We can take any redox reaction, and a sort of classic one is to take pyruvate dehydrogenase. Now, you know what the reaction is. Pyruvate plus NADH plus a proton goes to lactate plus NAD. And we can divide this into 2 half reactions. NADH goes to NAD plus a proton plus 2 electrons. Pyruvate plus 2 protons plus 2 electrons goes to lactate. You simply add these together mathematically and the electrons cancel out. Pyruvate plus NADH plus a proton goes to lactate plus NAD. Okay, 2 half reactions. Now, if we were dealing with physical chemistry, we would have some wonderful setup looking something like this with salt bridges and hydrogen, platinum, hydrogen electrodes, zinc anodes, and everything like that. And basically, that's what we're sort of doing when we're measuring redox potentials, except we don't actually do it this way. But we have to define a 0 point. And the 0 point is defined as the standard hydrogen electrode. And the standard hydrogen electrode is when you bubble hydrogen at 1 atmosphere over a platinum electrode in 1 molar acid. And that's defined as 0 millivolts. And everything is in relation to this 0 millivolts. Excuse me. So when I talked at the beginning that electrons enter complex 1 at minus 300 millivolts, that's relative to the standard hydrogen electrode, 0 millivolt hydrogen electrode. When I say the electrons leave to reduce oxygen to water at plus 800 millivolts, then that is relative to this standard hydrogen electrode of 0 millivolts. Now, the actual redox potential depends on how oxidized or reduced species are. The more reduced they are, the more negative the redox potential. The more oxidized oxidized reduced couple is, the more oxidized the redox potential. This is quite important because we can take the example of the NAD-NADH pool and the NADP-NADPH pool. And these have the same midpoint potential, the same half reduction potential at about minus 320 millivolts. In the mitochondrial matrix, the NAD-NADH pool is about 10% reduced. So in other words, the oxidized is 10 times more than the reduced. That drops the redox potential by 30 millivolts to minus 290 millivolts. On the other hand, the NADP-NADPH pool, about 99% reduced, that changes that redox potential to minus 380 millivolts. So even though they have the same midpoint potential, you have to consider the extent of oxidation of the pools. So the NADP-NADPH pool is much more reduced than the NAD-NADH pool. Just trying to look at people's faces here. A rather disturbing number have put on something anonymous, which I hope they haven't just gone away and discussed. Let's have a look. See who? No, there's still people there. That's good. Okay, people are still alive. Anybody totally confused at this stage and wants clarification, or can we continue slowly? We'll continue slowly. It's good. Now, the next thing is that midpoint potentials, half reduction potentials, are distributed down the electron transport chain so that concentrations in oxidized and reduced forms are roughly comparable. So it's roughly, so cytochrome C is roughly half reduced. Ubiquinone is roughly half reduced rather than 1 part in a million or anything like this. And this is important because you need the oxidized form to pick up electrons, you need the reduced form to release electrons. So they should both, for kinetics, be present at comparable concentrations. And this is what you find when you work your way down the electron transport chain. Now, we talked about redox potential differences, and basically the redox potential difference between two couples, the redox span, can be converted directly into Gibbs free energy by using this thing called the Faraday constant, multiplied by the number of electrons. One electron dropping through 1 volt is equivalent to almost minus 100 kilojoules per mole. Negative means that it's a spontaneous reaction which can occur spontaneously. So each electron dropping through 1 volt in the electron transport chain is equivalent to almost 100 kilojoules per mole of Gibbs free energy. And what we have for our traditional 2 electrons falling through 1.16 volt from the NAD-NADH couple to the oxygen-water couple is equivalent to about minus 224 kilojoules per mole. Now, we shouldn't really compare energies quite so specifically as this, but we know that the maximum number of ATPs you can make from NADH is 2.7 ATPs per 2 electrons. If each of those under operating conditions is somewhere up about nearly up 60 kilojoules per mole, then the amount of energy you're getting out is about 155 kilojoules per mole. So you're within a reasonable range, but don't get too tied out with trying to work out efficiencies. You go into the textbook and they use the standard Gibbs free energy for efficiency, which will come out to roughly half the real value. Okay, we are whizzing through this, and I do hope that you have questions to ask, and that because I'm putting so much information and giving you so much heartache after you've thought for the last 15 years that ATP was a high energy molecule. You must be very disappointed. That will go on to the third component now, which are ion electrochemical gradients. And this is obviously the proton gradient is part of this. And this again starts looking complicated and ends up beautifully simple. And this really states it. So you have a membrane. You know, the membrane can be a bit of plastic with some transport process embedded in it. And we know that Gibbs free energy is displacement from equilibrium. We know this. And if you measure the concentration of our compound X on one side of the membrane, concentration of our compound X on the other side of the membrane, and you work out the ratio, that is the displacement from equilibrium of X across the membrane. And the Gibbs free energy, this is 2.3 RT log to the base 10 of the displacement from equilibrium, in exactly the same way as it was for the standard Gibbs free energy, or for the Gibbs free energy equation for a scalar reaction, where it was equilibrium constant divided by observed mass action ratio, displacement from equilibrium. No surprises there, it's exactly the same principle. How far you are from equilibrium in terms of a concentration gradient is exactly the same as how far you are away from equilibrium in terms of an equation, a scalar equation, enzymatic equation. Now, if you forget the concentration gradient and you have you have instead a membrane potential. And remember what I said about the membrane potential. The membrane potential is shorthand for the difference in electrical potential between two compartments separated by a membrane. The Gibbs free energy is given by the number of charges on the compound under the ion under consideration, our friend the Faraday constant, and the membrane potential. So this is a situation, no driving force due to a membrane potential, just due to a concentration gradient. This is the driving force due to a membrane potential without considering the concentration gradient. And so it's fairly intuitive that the total driving force is going to be the sum of the two. So it's going to be that plus that. And this is hideous. It looks a little bit similar to the standard Gibbs free energy equation, which I hate. So we're going to make it simpler. And the way we're going to make it simpler is to look at one particular gradient, the proton gradient, and to look at the proton motive force and how to derive this. We're going to do this very simply. This is the equation which looks horrible. Oh, terrible. Driving force due to membrane potential, driving force due to disequilibrium across the membrane of this charged species X with M positive charges. That's where that M comes in, the number of positive charges. Now, if we're dealing with protons, we have two simplifying factors. The charge is 1, so M equals 1, and we have this strange thing called pH. The negative logarithm of the proton concentration is called the pH. And so we have a logarithm there, but the pH is a logarithm. So the thing simplifies to this reaction. The Gibbs free energy change, and now we're calling it the proton electrochemical potential gradient, long word, in kilojoules per mole, is minus the Faraday constant times the membrane potential plus 2.3 of this thing. So it's a factor of the membrane potential and the pH gradient. And this is in kilojoules per mole, and this is thermodynamically correct, and this is directly equal to the Gibbs free energy. This is another way of the Gibbs free energy. Gibbs free energy is that. But what Mitchell introduced, what is extremely useful and we all use, is the realization that we're looking at something which is electrical. And in electrical units of potential, we use volts or millivolts. And we can convert this from kilojoules per mole to millivolts basically by dividing by the Faraday constant. This very useful thing called the Faraday constant switches you backwards and forwards between millivolts and Gibbs free energy kilojoules per mole. And when we do this, we end up with something we call the proton motive force, delta P. And the proton motive force is delta psi minus 61 delta pH. And that's the equation which we're going to be working with for the rest of this 2.5 days or so. Those who are very alert will realize I'm a little bit sloppy with this number. Sometimes it's 59, sometimes it's 61. This is just at different temperatures. 61 is the most accurate at 37 degrees Celsius, 59 at room temperature, but yeah, we're not going to quibble over the difference between 59 and 61. This is the equation. You have derived it, you understand it, how it came about. So, 9th take-home point. A typical mitochondrion maintains about 150 millivolts of membrane potential, a delta pH of about minus 0.5 units, proton motive force under conditions not really making much ATP is close to 180 millivolts. Martin has a clever trick working in a potassium grade medium that he adds a potassium ionophore nigericin, a potassium proton exchanger, and that effectively converts the residual pH gradient into a membrane potential. So he would measure a membrane potential of 180 millivolts and a delta pH of virtually 0. So that would be the same. So how do we link these three forms of Gibbs free energy? Biochemical reactions, redox reactions, and ion electrochemical gradients. The proton circuit is what links the three of these. So we have come at a fair rate, actually. We're ahead of time, but let's just spend a few minutes recapping. We use Gibbs free energy rather than entropy because it means the same thing, but with entropy we've got to measure what happens in the rest of the universe, and the universe is big. That even though we call it equilibrium thermodynamics, it's really thermostatics. It deals with equilibrium conditions and how far away from equilibrium you are, and how far away from equilibrium gives you capacity to do work. ATP is not a high energy molecule. It's the ATP hydrolysis reaction, which can be driven up to 10 orders of magnitude away from equilibrium, that gives this capacity of the ATP hydrolysis reaction to do useful work. Okay. You can use the stupid equation ATP goes to ADP plus phosphate as long as you define the equilibrium, as you define the conditions and the equilibrium constant conditions to be identical. So you've got to measure the concentrations, look up on a table what the apparent Gibbs free current equilibrium constant is under those conditions of magnesium, etc., and then you can get away with it. Oxidoreduction reactions are always electrons, even if protons follow later. It's always the electrons that are important. You define everything with respect to the standard oxygen electrode at 0 millivolts. The standard I'm getting confused here. Standard hydrogen electrode at 0 millivolts. No wonder you get falling asleep. I'm falling asleep here. And that gives you potentials ranging from about -300 or 400 millivolts to about +800 millivolts or so. And this is critical for following any bioenergetic reaction. The more reduced a couple, NADH and NAD make a couple, NADPH, NADP make a couple, oxidized reduced couple. The more reduced a couple is, the more negative its actual redox potential. When you move on to ion gradients, two driving forces, concentration gradient and membrane potential difference across the membrane. In the general case, you just add them together. And if you're dealing with a proton, the whole thing simplifies very beautifully to delta P is delta psi minus something like 61 delta pH. So I think we're there, except that it's all in chapter 3. Everything I've talked about basically is in chapter 3. So you have that source to go back to. I have long ago given up trying to get royalties on on the bioenergetics 4. Virtually every university now has a site license for it, so you can download individual PDF chapters, perfectly legitimate. I am very happy that students pirate it because it's much more important that they get the information rather than they get 42 cents for a copy or whatever ridiculous sum that it actually is. Okay, I stop there. And Ricky, are you with us?
Is there any questions on that before we move on?
Yeah, I have a minor question. So I mean, you've mentioned a couple times the effect. I mean, you showed the effect that pH and magnesium concentration have on equilibrium constant for these reactions, and there are tables of what that might be.
Yeah.
Where do we find these tables, and are we only really supposed to be concerned about pH and magnesium?
pH, it's everything you measure. And pH, in the specific case of the ATP hydrolysis reaction, it's the pH and magnesium that are the most important. The tables, let me think. These go back many, many years. This was mostly
papers by Williamson, John Williamson, who
and Bill Slater as well.
Slater and Chance were also doing it. So you can find in the literature exhaustive several page tables which go through all the different variables and the measurements of them in different places. It's almost inconceivable that you would want to, or that would be useful.
Maybe, but I can't help but be curious as long as these tables were mentioned a couple times.
Yeah. If you go on to PubMed and put in Slater EC Slater, then, and you go back to sort of early 1960s, you'll find a few of the key publications with tables in it.
Because those people were trying to unravel the thermodynamics of the system by making accurate measurements of things. And they realized you can't just measure ATP, even though lots of nature papers these days do that. You have to measure ATP and ADP and phosphate. You have to take into account the compartmentation within the cell of those things. Then you need to know the pH in the different compartments. You need to know the free magnesium, the free potassium, the free calcium, any small concentration divalents and trivalents like Fe, all of these equilibria. And you need to know the ionic strength and the onconic strength. And the list of the variables that you need to know just goes on and on. And I think what these guys got to is, this is too difficult. So we can get an approximate answer to the thermodynamics, and it kind of works. And then they moved on and did other things. So analytically, it's not really a solvable problem in a real biological system.
So to that, like when someone measures ATP in vitro, I mean, there's probably also a big danger of it's a lot of it being converted to ADP. So how do you ever get an accurate measurement? You're saying this is the best, the proxy would be the best way rather than ever measuring ATP, ADP, or in other words, would there be any value to measuring ATP, ADP, or are there right ways to do it?
I think David covers this in one of your next lectures, don't you, David?
I should do, yes.
But
basically, I mean, yeah,
it's really hard to measure. If you measure ATP, you're making a fool of yourself. at the very least, you have to measure the ATP-ADP ratio. But you're still ignoring compartmentation, which,
and
as
phosphate.
David showed you, the ratio is 100 times different in the matrix compared to the cytosol. So you're getting some average of those two.
Right.
Even if you measure both ATP and ADP, you're kind of in great danger.
But
in general, it's much better to measure the membrane potential because
Right.
it's easier to measure and it doesn't have all these problems. And it tells you the same thing.
And even if you were to measure the ATP-ADP ratio, I'm just wondering, like the whole preparation process, wouldn't that mess up the ratio, given it's so, like you said, it's how many, the equilibrium constant so shifted towards ADP.
Well, the thing is, it's so labile, and I'm actually going to talk about this in my final rant, which is where I say what's wrong with the field on Wednesday, if you're still with me then. And the essential thing is you've got to quench a reaction instantaneously.
Yeah.
You've got less than a second to kill everything and freeze the equilibrium. Otherwise, everything's going to collapse. You can't centrifuge down cells because they go anoxic, and everything changes, for example.
So I use that as my criterion for judging metabolomic papers. I just look at the ATP-ADP ratio that they measure, and they generally find it's near the equilibrium value, which David was talking about, of 1 to 1 million, or at least they don't usually find it quite that bad, but it's maybe 50-50 or something.
Oh.
And you can tell that they haven't handled their sample right if that's what they find.
Yeah, I'm going to give that exact example on Wednesday.
Yeah.
I had a question regarding redox potential and sort of looking at that as well, since we talked about the halfway point versus, the midpoint versus the half cell.
Hang on, who's talking here?
This is Carl.
Okay, Carl, so you can see you.
Hi.
Sorry, carry on.
So my question was sort of how does that, because the ratio between NADPH and NADP is also going to vary depending on the compartment that you're looking at.
Oh, yes.
But it is also very strongly tied to mitochondrial function. And so I'm sort of interested because a lot of, as to sort of those two come into play, say you're looking at seahorse, or how does that get analyzed and sort of the importance on, like we said, quenching for something that is as quick as disulfide bond shuffling, which occurs, for protein folding and causing, stress.
So what's the actual question? Sorry,
So my question is there sort of a way to look into using that ratio or the changes in the compartmentalization as a way to look at perturbations in mitochondrial function and how tightly those two are regulated?
Yeah, do you want to talk about this, Martin? You're doing NADH fluorescence at the moment.
So in principle, what you're measuring there is a level in a dynamic system of rates and levels. And all of these things can give you information if you measure them right. So measuring the protomotor force tells you something about the system and can give you some entry point into looking at function, but it's not in itself a measure of function. Same with the NADH-NAD ratio or the NADPH-NADP ratio, as long as you measure them correctly. The problem that we were leading from is that it's really hard to measure them correctly. So because of the compartmentation and because of the lability of them, if you do it by putting your rat liver on a bench, going and have a cup of coffee, come back, mash it up, extract it, forget it. You're measuring some sort of near equilibrium soup. So you need some either very rapid quench mechanism, and usually those are incompatible with working out the compartmentation. So it's quite hard to both stop quickly, say freeze it, and also know which compartment to look at. So in the end, it's often better to use some sort of fluorescent or photometric assay using a genetically encoded probe, for example, in a particular compartment, which is talking to the intermediate you're interested in this case, say the NADPH-NADP ratio.
Yes,
and if you have a really good one that works and you use it properly, then that can be very helpful in knowing what the level of that particular intermediate is. But it still doesn't tell you function, because that depends on the fluxes and how you define function.
Does that include a
sorry,
as well?
For example, to give you an example, the NAD-NADH pool is about 10%, 10-20% reduced in mitochondria under most conditions. In the cytosol, it's about between 0.1 and 1% reduced. So it's enormously oxidized and very different. If you homogenize a cell, you're going to get some random mixture between the two. The same way as if you measured ATP-ADP ratios in an intact cell, you get a random mixture between the two. One way you can get these extreme ratios, for example, for NAD and NADH, is you can measure lactate pyruvate ratios. And then you know the equilibrium constant for lactate dehydrogenase. And if you measure an accurate lactate pyruvate residue, you can then work out what the NAD-NADH ratio would be to produce that ratio. This has been used quite extensively, this type of approach.
Mm-hmm. I've seen that used to measure cytosolic NAD and ADH. What about mitochondrial?
Which one would you use for mitochondria? If
there's
you
two
liver
ways.
mitochondria,
The classic way is to measure the beta-hydroxybutyrate acetoacetate ratio in those tissues that have the beta-hydroxybutyrate hydrogenase, because that's exclusively in the mitochondria, so it's only talking to the mitochondrial NADH-NAD ratio. The other way to do it is by a piece of good luck, and that is that the fluorescence, the autofluorescence of NADH in cells turns out to be very strongly enhanced by binding to particular sites. And it turns out in most cells that particular site is complex 1. So if you measure the autofluorescence of NADH, it mostly reports the mitochondrial NADH-NAD ratio, or the NADH level. And then if you do the dynamic range of fully oxidizing and fully reducing, you can work out what the ratio must be. So it is possible to get at it with a few caveats and a few excuses, but it's not really what you want to know, but it's a surrogate of what you want to know. So we measure it still routinely, the autofluorescence signal in cells, to estimate the NADH-NAD ratio in the mitochondrial matrix.
So I had a question based on what you just said.
Yeah.
So if you're going to measure NADH autofluorescence in, let's say, a beating heart, would you be looking selectively then at your mitochondrial NADH pool based on, you know, that it's binding and the fluorescence is enhanced when it binds to complex 1?
Yes, most of what you see is that. There are different estimates of how big most is, but it's at least 80%, 90%. That's where it's coming from.
Okay.
And you do see the other things, and you can sometimes do controls to get rid of them. For example, you can set the lactate pyruvate ratio to different values, which the mitochondria won't care about, but the cytosol will. So the part of the signal that responds to that is actually coming from the cytosol. But it turns out to be relatively small, 20% or so of the total.
And also the cytosolic pool is so oxidized it won't contribute. The problem is the NADP, NADPH pools, and it depends on what your cells are, as how much of a confusing factor that is, because the fluorescence is identical. You can't distinguish.
So there are two ways to deal with that problem. One is, as David mentioned, the transhydrogenase drives the NADP pool much more reduced. So actually it doesn't change very much as the NADH-NAD pool changes. The NADPH-NADP pool also changes by the same extent, but it's going from 99 to 98% reduced instead of 50 to 10% reduced. So the NADPH signal is pretty constant. So mostly you can just pretend it's background and subtract it. And then the other way is there are some fancy spin relaxation methods that you can use to distinguish the two pools. So the NADPH fluorescence has slightly different relaxation properties from NADH fluorescence. And if you have the right equipment, you can tell them apart, but we don't do that routinely, but it can be done.
Okay, you got it.
Okay, so this is the more complicated network of ion fluxes. And the question we want to address is, well, what determines how fast this system runs? In particular, what's determining the rate at which oxygen is being consumed when you run the proton circuit, when it's integrated into all of the rest of these things. And a good way to demonstrate that is to get you involved here. So I want you all to do something for me, even if you feel embarrassed and you're in front of other people. Can you all stand up and jump up and down? And I can see you on the screen, so I know if you're doing it. So a bit of jumping. Everybody? Very good. Okay. That's my exercise for the day, by the way. Okay, what just happened there? Think about it. What happened? I control your rate of oxidative phosphorylation in your skeletal muscle mitochondria. So the answer to the question, what controls the respiration rate of mitochondria, is Martin Brand, sitting in San Rafael in California, controls the rate of respiration of your muscle mitochondria. That's a true statement, right? It just happened. But you can sit there and say, no, that's unfair. It wasn't Martin that controlled it, it was me. I did the jumping up and down. So no, let's leave Martin out of this. What controlled the rate of my oxygen consumption was me. I made a decision. So it's my brain that determines the rate of oxidative phosphorylation in my muscle. Okay, and your muscle's sitting there thinking, that brain really is a bit ahead of itself here. Because it was me that did it, right? The muscle, some nerves sent down a signal, some calcium came out of the sarcoplasmic reticulum, and that caused the myosin to contract, and that caused a change in the ATP-ADP ratio in the cytosol, and that's what changed the rate of respiration of the mitochondria. So the brain is overthinking. It's really not an important player here. What's important is the ATP concentration in the cell. So in your muscle cells, what happened was the ATP concentration changed. And that's why your respiration went faster. So which of those explanations is right? And the answer is they're all right. Each of those descriptions is a completely correct description of what controls the rate of oxidative phosphorylation in your muscle. And that leads me to really the idea of the boundaries of the system. So you cannot ask the question, what controls the rate of something, unless you also define the boundary conditions of your system. If I'm included in your boundary conditions, then I was the one controlling your rate of oxidative phosphorylation. If you leave me out, then it was your brain. If you leave your brain out, it was your nerves conducting impulses to your muscles. If you leave them out, it was the calcium. If you leave the calcium out, it was the ADP-ATP ratio. All of them are valid, and the boundaries determine the answer. And you can get very different answers depending on your boundaries. So in the answer to the question, what controls the rate of oxidative phosphorylation, is an unanswerable question. You can only answer that question if you define the system or define the boundaries of that system. And you're going to get very different answers. So if you look at isolated mitochondria sitting in a pot, the answer you're going to get is going to be very different from if you consider a muscle in situ or an animal wandering about in the wild. And yet they're all valid answers. So you need to define the boundary system. So these are covered by this idea of global or regional or local or very local. So whether you're sprinting or resting is a determinant of the rate of oxidative phosphorylation in your muscle. Whether you consider the whole muscle or individual fibers determines the answer. And what we're generally going to do is be very reductionist. And we're going to consider only isolated mitochondria with fixed substrate supply. And the reason for doing that is it's very simple. And we're going to get a simpler answer back. But it's also less physiological. So in some of the practicals and in some of the discussions, we're going to at least go up one level and consider what happens in cells, because the boundary is different and therefore the way that the control is exerted can be different. And then the second thing to remember is time domain really matters. And it took me a while to fully understand, and I hope I do now fully understand why time is so important. But if you take isolated mitochondria in a test tube, or you put them into a seahorse, and then you ask the question, what changes the rate of this system? The answer you're going to get depends entirely on forces. So forces as in thermodynamic forces, the delta EH, the delta G of the systems, and that can translate into concentrations, which are chemical forces. So what controls the rate of isolated mitochondria in a seahorse is the various forces in the system. The added ADP, the chemical potential that you impose on it, whether you have uncoupler there, so whether you're changing the proteomotive force by uncoupling, that's the determinant of the respiration rate. If you step back a bit and you put some cells into the seahorse instead, you change your time constant. Now you're certainly in minutes and often in hours or even days, you're looking at a different region of time. And if you look within minutes, then the machinery starts to matter. So for example, you might trigger some phosphorylation cascade in the cells, which changes the supply of the substrate to the mitochondria. And that now becomes part of your system. You've expanded the boundaries to include things that can happen over the time that phosphorylation cascades happen, over minutes or tens of minutes. If you work fairly rapidly, you don't have to worry about changes in gene expression because they take several hours usually to fully manifest. But if you're working with cells in a dish and you're doing something and then measuring the next day, then clearly transcription, translation of nuclear messages becomes an important part of what's going on in terms of regulating things and changing the rates of things. So if you have cells in a dish, you do something, you come back the next day, then the machinery has changed. Your mitochondria might have got more proteins or changed in volume density, or there might be new proteins in there. And all of those can change what's going on. And your description of what's controlling things is very different from the instantaneous seahorse experiment. And so we end up often in this slight contradiction that the sort of question we're asking is, what does my gene do to oxidative phosphorylation? Or what does my drug treatment of an animal do when I measure 48 hours later to the rate of oxidative phosphorylation? But the system we're using to measure it is one which responds in seconds. So we're usually using a seahorse, or we're using a measurement of membrane potentials in a microscope, or we're measuring some metabolites. And very often we're looking in this time domain. So we're using this time domain to try and understand this one. And that can lead to a lot of complications, which don't need to be there if you're clear thinking about it. So in the next lecture and the next two lectures, I'm really going to be concentrating on this very short-term, over seconds time domain, and looking at a very local level, either isolated mitochondria or cells. And we're trying to interpret what we see in terms of these other domains, either hours and days, or these organ level and global level physiologies that are going on. And as long as you remember you're doing that, you can make quite a lot of headway in understanding the problem. But if you don't remember that, you can get really confused about what regulates oxidative phosphorylation. Is it the P53 concentration? It depends on the time, and it depends on the scale that you look at as to whether that's part of your system or not. So either it does or it doesn't. And in these next two lectures, I'm going to be considering the instantaneous changes, so it doesn't in those instantaneous changes. But I work in an institute which is focused on aging. And what we're interested in there is, at least for humans, is processes that change over decades. So we're often asking the question, maybe using mouse or rat models, of what's the difference between a young animal and an old animal over 3 years, say. And there, it's chronic changes in the machinery, which are the dominant thing that we're interested in. And of course, often we're interested in evolutionary differences. So we're comparing naked mole rats to laboratory rats, and we're saying, how are they different? And there, the driver is something that's taken place over millions of years. And we're trying to understand by measuring over seconds how that plays out in a dynamic control. So remember what the boundaries of your system are for the question that you're trying to answer, and make sure that the boundaries you set are appropriate for the question that you're trying to answer. And remember what time domain you're really interested in. And remember that the methods that we use for understanding what's going on are usually very short time scale measurements, but we're usually trying to understand things which take place over minutes, hours, decades, or eons. If you keep those differences clear, you can make a lot of progress. So then what controls the rate at which mitochondria in a dish in the instantaneous time domain actually operate? What determines the oxygen consumption rate of isolated mitochondria moment by moment? And the answer is it's very simple. The rate, which is usually given the symbol J, is some function of a rate constant and some forces. So it depends on the catalytic constants of the machinery that you happen to have in front of you, or you put into your seahorse or your Ouroboros. So those are constants in this short time domain, but these are the things that gene expression will change over longer times. And it's the driving forces, which, as David explained, is the displacements of reactions from equilibrium. So these are all Gibbs free energy functions. So what determines the rate at which a process runs is some function of these rate constants and the driving forces. And as David explained, what's normally considered to be thermodynamics is really thermostatics. It tells you what happens when nothing is happening. But there's a branch of thermodynamics called irreversible or non-equilibrium thermodynamics, which is not static, which is genuine thermodynamics. And it turns out that this general relationship, most of the time, for reasons that the theoreticians argue about, most of the time actually becomes a simple linear function. So the underlying principle of irreversible thermodynamics is, for a given kinetic constant, how fast something goes is a linear function of the delta G of the reaction. So if you double the delta G, you double the rate. And that is not so intuitive, but it turns out empirically to be very true for limited extents of displacement from equilibrium. And so close to equilibrium for most systems, the rate of a process simply depends on how far away from equilibrium the various driving forces are. So what's your ADP to ATP ratio? What's your succinate to fumarate ratio? What's the protomotive force? Those are the determinants of the different rates that are going on within oxidative phosphorylation. And then the other formulations of that you're probably familiar with are really just different expressions of that same idea. So Michaelis-Menten kinetics simply says that the rate of an enzyme is some constant, it's the Michaelis constant, multiplied by a force, in this case a chemical force, which is the concentration of the substrate at zero product concentration. So below the Km, that's pretty linear, so it follows non-equilibrium thermodynamics. And then as you raise the rate, it moves into this non-thermodynamic, non-equilibrium thermodynamic domain, where no longer is it a linear function as the enzyme saturates. So gradually you end up with a saturated enzyme and a Michaelis-Menten relationship between the forces and the rates. But at most biologically interesting concentrations of metabolites, you're working below the Kn of the enzymes, so you're working in this linear region of the rate constant times force relationship of Michaelis-Menten kinetics. And David also mentioned Ohm's law, so from electricity, where the forces and the flows behave in pretty much the same way, the current is simply a constant, 1 over the resistance or the conductance, multiplied by a free energy term, the voltage. So V equals IR is Ohm's law. It's a linear relationship between the displacement from equilibrium, that's the voltage, and some constant, which depends on the properties of the system. How thick your copper wire is would be the case for Ohm's law. So these are all expressions of the same general idea, and that is how fast something goes depends on the kinetics, the constants set by gene expression or by physics, and the forces that are involved. And if you work in these very narrow time domains, the kinetic constants are constants, they don't change. So you're only interested in the forces. If you work in systems where gene expression or phosphorylation cascades or evolution can occur, then those things work by changing those rate constants. And you get a very different picture of how the process is controlled because your focus is on how the rate constants is changing. And you only really need to worry about the forces when you actually do experiments. So when you do experiments in the seahorse, you're suddenly back in this domain of seconds. And suddenly what your question was, which is, how did my gene expression change the rate constants? You suddenly are presented with something that changes rate when you change the forces. And it's important to remember that both of those things are true and both of them are determinants of the rates. So that's summarized here at short time scales. The flux changes depend on the forces and nothing else, because you're given a bunch of kinetics. That's what you have in your tube. At longer times, the kinetics can change because you're doing things to protein expression or to post-translational modifications of proteins or the amino acid sequence of your proteins. So you're changing the rate constants, and that's the molecular biologist's view of what's controlling things. And in terms of the everyday electrical analog of your home, you can ask, what's controlling the electricity use in your home? Is it whether you have the lights switched on or switched off? So that's the forces. You're allowing the circuit to run or not run. Or is it by having more light fixtures? If you go out and buy 10,000 light fixtures and light up your house like a candelabra, that'll control your electricity use. So that's the gene expression part of the equation. And you need to think about which one you're interested in. Is it the dynamic short-term changes or the amount of light fixtures that you really care about for your particular question? So in terms then of our chemiosmotic proton circuit, the fluxes are determined by the forces. And the forces are the substrate concentrations, how much succinate do you put into your tube, or how much glucose is the cell taking up. And then by the other forces within the system, the difference in the redox potential between the succinate and the oxygen, or across complex 3 between the ubiquinone pool and the cytochrome C pool. And the forces across the membrane, the proton motive force, the membrane potential and the pH gradient are determining the ion fluxes across this membrane. And they're in turn determined by the redox fluxes, the redox potentials, which are driving that proton pumping. So the QH2 cytochrome C redox poise is driving the proton flux across complex 3, and complex 3 pumping is driving the value of the proton motive force. And then all of these things are driving the delta G component, the chemical potentials. In this case, the phosphorylation potential of the ATP-ADP phosphate couple are being driven through these proton motive forces, through the redox forces, and by the externally applied driving forces that you've got in your particular in vitro experiment, where you're in your seahorse, you're adding succinate or glucose or whatever your substrate is. You are in principle controlling the oxygen tension, and then you're changing the amount of ADP that the system is seeing by driving different processes that are able to hydrolyze ATP to ADP. So when you put your mitochondria or your cell containing mitochondria into an Ouroboros or into a seahorse, what you're doing is you're saying, okay, we measure some rate or other, which is set by the kinetics and the standard driving forces, and then we're going to poke at these forces by adding oligomycin to prevent the ATP synthase from running. And that changes all the forces, so the changes, you see changes in rate, or we can inhibit the electron transport chain and we see changes in rate, or we can uncouple the membrane by adding FCCP, which changes all these forces, so we see changes in rate. So what you're doing there in the instantaneous time frame is you're changing the forces and you're asking, how does the system respond? And then what you can do in terms of the wider molecular biologist question is you can say, okay, what can I infer about the nature of the rate constants, those K values in the equations, from the way that the rates change when I fiddle around with the other forces in the system? So can I infer that the electron transport chain has been rendered less functional, inhibited? by the way it responds when I poke it with all these different changes in forces in my experimental system. So in the end, often what you're doing is you're trying to infer things about what your changing protein expression did by the way that the dynamic system responds when you impose different forces on it and ask it to change rate. So then as an experimentalist, you have some constraints on you, and you have some different systems that you can use that have advantages and disadvantages. And you really need to make a careful choice about what system you want to use to answer your question, depending on what your question is. And in general, the more reductionist your question, the more mechanistic your question, then the more simplified your system needs to be. So if you want to understand the mechanism of complex 3, you don't start in the field with a cow standing in the field. You dismantle the cow and you take it down to just that complex or just the mitochondria containing that complex, and you put them in a dish and then you say, how does this work? So you take a very reductionist approach. And in terms of bioenergetics, what that usually means is you work with isolated mitochondria. Sometimes you purify out the components and you ask how they work. Question? Somebody needs to mute, probably. Please.
我就在这儿听了就行了。他酿葡萄酒呢。
他这是做西瓜，本来是种西瓜。
不是葡萄吗？
I've got control. I can mute Jingqi. So if you want to study a sufficiently complicated system that it's bioenergetically interesting, but one that's not so complicated that there's always complication that will stop you from being able to do the things you want to do, then you would use isolated mitochondria. So isolated mitochondria are relatively simple. Am I still with everybody? I just did something to my screen.
No, we still see you.
So isolated mitochondria are pretty simple, pretty well understood. And if you want to understand the mechanism of your particular pathology or your particular drug action, they're a good place to start. The difficulty is if you try and do physiology using isolated mitochondria, because the cell is not there, so you don't have the physiology. So if your question is more physiological, how do the mitochondria interact with the Golgi, then clearly you need to be working in a more complex system. So there you would work with cells so that the Golgi is present and you have an undisturbed cellular environment, which is of greater physiological relevance. Although, as I was commenting to some people in a breakout room just now, cells are also not physiology because they lack the context of the organism. Isolated mitochondria are pretty easy to isolate from tissues or from genetically modified animals. But the big problem is you inevitably damage them when you isolate them. So you're working with a damaged organelle, which has been ripped out of its normal physiological context. There are bits of proteins that it used to attach to the rest of the cell with, dangling on the outside. There are bits of machinery which are half working and half ripped apart. So there's really a lot of nasty stuff going on in an isolated prep. And if you care about the interactions with the cell, isolated mitochondria can be a pretty confusing system. If you work in cells, you don't have all those artifacts and you can do things within the cells. But at least historically, it was quite hard to isolate a particular cell type from an adult animal. Although that problem is being mitigated these days by stem cells, which you can differentiate into the cell that you're interested in, as long as you believe that it's the same as the cell that you're interested in, not just a weak copy of that cell. And then a huge advantage of using isolated mitochondria is you have control over the conditions in your experiment. You can add a whole range of different reagents and substrates, and most of them or many of them will go straight into the mitochondria so that you can directly probe all the different components of the electron transport chain. The corresponding disadvantage is you have to choose right, because if you choose some stupid incubation condition, you're going to get back an answer which is relevant to that incubation condition and not relevant to the cell. So the way to overcome that is to go into cells where the cell worries about that stuff. So you just take a cell, you grow it, and the inside of the cell is up to the cell to determine what's going on. So it sells that environment. But in the process, you lose a lot of flexibility. So now you can't add a whole range of substrates that you want to add because the cell is looking after those things. And then the cell is trying to resist the things that you do. So you make a change and the cell says, I don't like that. So it makes a corresponding change to make it go away again. So particularly over a longer term, you get gene expression feedback where you change something, the cell senses it, it changes its suite of gene expression. So it changes the kinetic constants in the mitochondrial system and changes the system to try and keep homeostasis, keep what it was doing before. So the cell will resist you if you work in cells, but in isolated mitochondria, there's nobody to resist you. You're the king and you can do what you want. And as long as you do sensible things, then you have good control over it. Historically, there are good methods for isolated mitochondria, but you need buckets full of material because that's the way that we used to work in the 60s and 70s and 80s. When you switch to cells, nowadays there are more and more methods becoming established, and you can use tiny amounts of stuff. So increasingly, cells are a better way to do a lot of the physiologically relevant biology, but it's still worth going back to the mechanistic simplified system to really pin down what's happening and whether you correctly interpret what's going on in the cells. And then finally, a slightly strange one, that with isolated mitochondria, normalization is pretty straightforward. So you dump 2 milligrams of protein into your bucket biochemistry well, and you just say per mg of protein, this is what goes on. And whatever the cells do, that's lost. So if your cells proliferated in response to your treatment, you don't care because you pull out the mitochondria and you normalize it to per mg of protein. So cells changing the amount of mitochondria is invisible to you. And that's a good thing if you're trying to understand mechanism. It's a bad thing if you're trying to understand that cell response, which is a proliferative response of the mitochondria. The inverse of that is if you use cells, then all of these different things the cell may do are retained. So now if you normalize per cell, you're going to get an answer which gives you a different rate depending on how much the mitochondria have proliferated in that cell. Whereas if you normalize per mitochondrion, you lose that. So how you normalize matters a lot when you use cells, and it really doesn't matter very much when you use mitochondria. And the meaning of the results in cells changes depending on how you normalize. So if you normalize to cell number, your change in rate between your normal control and your treatment tells you that the amount of respiration per cell has changed. But that might give you a very different answer from if you asked the same question and said, how much did my rate change per amount of cell mass? Because if you have a lot more cytosol, one of them will change and one of them will not. So how you normalize matters for how you interpret the experiment when you use cells. Okay, so how do you measure the rates? And primarily we're interested in the rates of oxygen consumption. But we're also interested in measuring the forces because that, as David said, gives you more precise information about what's going on. So when I first went to undergraduate classes, there were still Warburg manometers in use, which measure the change in the volume of oxygen in an atmosphere. So if you have a fixed amount of atmosphere trapped in a vessel, and then your biology consumes some oxygen, then up to 20% of that volume can disappear as the oxygen is absorbed and used. Obviously, if it's converted to CO2, then some of it comes back. And you can measure those volume changes or pressure changes using a manometer. So it works, it's clunky. And then when I started my PhD, Clark electrodes were just coming in. So these are ones made by Rank or Hansatek, Yellow Springs, and the Ouroboros, which is still being used by a lot of people, works on this same principle, where it's an electrolytic reaction. So you pass a current through a solution, and the rate at which that current flows and changes at the electrodes depends on the oxygen tension in the solution. So you consume a bit of oxygen and you measure the current that flows as you do that and convert that into a readout of oxygen tension. So although that's still available in various oxygen electrodes and in the Ouroboros in particular, these days, mostly people have switched to using fluorescent oxygen sensors. So they have the advantage of not consuming the oxygen, so you don't have to worry about oxygen being depleted during the measurement. And they have the advantage that you get a nice big fluorescent signal. And that's what's used in the seahorse, for example, or in the what we still call oxygen electrodes, but they're actually fluorescent oxygen probes that we use in place of the Clark electrodes in our lab. The disadvantage of these sensors is the response is nonlinear, so you have to be much more careful in how you calibrate them. And when you use the seahorse, you're relying on the seahorse algorithms correctly converting the fluorescence into an oxygen tension. And that's a contentious point which can give you problems, which we'll return to later on. To measure the proton motive force, historically, you could measure the membrane potential using radio-labeled probe distribution. And these days, again, mostly people use fluorescent probes, and David will spend a lecture talking about TMRM and how that's used in mitochondria and in cells to probe what the membrane potential is. Lots of pitfalls, but if you do it right, it can be really informative. And to measure the other component of the proton motive force, the pH gradient, as David said, mostly it's a pain, so we don't do it. We just pretend it's not there or that it's a linear function of the membrane potential, which it often is. But you really should measure it. And to measure it, again, you can use radio-labeled probe distribution. As David mentioned, you can use nigericin to convert all the delta pH to delta psi and then measure the delta psi. Or you can use fluorescent probes, such as genetically encoded probes, which you can place into the mitochondrial matrix and into the cytosol, and then use the two fluorescent signals to deconvolute to work out what the mitochondrial pH gradient is. And measuring the fluxes, allied with measuring the fluxes, gives you much more information. Yeah, question.
Yeah, I was curious, the ciphers, those ratiometric pH sensors that can be targeted to the inner membrane space or the matrix, have you used any of these at this point?
Yeah, we use them a little bit, and the older ones are very prone to pH artifacts.
Right.
So you have to be very careful with those. The newer ones, people are aware of that problem, so they're mostly okay, but it's still generally a good idea to check. So the problem with those is usually calibration and sensitivity.
Right.
So if you can't calibrate them, you get a qualitative signal out. And if they're not sensitive, you say nothing's happening, when in fact something interesting may be happening.
So I was also curious, it seems like there are circumstances where the cytosolic pH can actually change by quite a bit, by about like 0.2. For example, hyperglycemia is sufficient to change the internal pH of most cells. Do you ever notice alterations in the membrane potential with TMRM when the cytosolic pH changes? Because theoretically, that should also affect the dye incorporation into the mitochondria.
That would be true if the mitochondria had a mechanism of regulating their internal pH. They do have some mechanisms like potassium proton exchanges, which partially do that. But mostly they don't. Mostly they're just setting a delta pH. So if you make the cytosol more acidic or more alkaline, then pretty quickly the mitochondria follow suit and maintain about the same delta pH, but at a slightly different absolute pH value. So the absolute pH will affect what goes on, but bioenergetically it's only the delta pH which really matters. So the delta pH is the bioenergetically relevant parameter. The pH is part of the kinetics, part of that rate constant, and can change the catalytic activities of things. So both of them matter, but for the bioenergetics, the delta pH matters much more. And in general, the mitochondria just follow the cytosol and do whatever it's doing.
I guess what's also confused me is I've seen a lot of experiments from Tobias Dick's group where they use the Rho GFPs targeted to either the cytosol matrix or inner membrane space. And under alterations where the reducing potential of the cytoplasm is increased, so like glutathione treatment, the mitochondrial matrix seems to actually become more oxidizing to the Rho GFP, which has really confused me with regards to the kinetics of those equilibration moments.
Yeah, so this then will quickly degenerate into a methodology discussion.
Right.
So the general response is you have to be really careful with your methods before you infer that those things are happening. And I'm not persuaded that those things are really happening, that it's not a methodological artifact.
Got it.
It may be, but it's really hard to know.
Yeah.
Okay. So here's the mitochondrial respiratory control experiment that David showed briefly. And I want to build the rest of this lecture on this trace and trying to understand what's going on. So here we're measuring the oxygen concentration in a suspension of mitochondria, or if this was a seahorse, we'd be measuring it in a monolayer of mitochondria spun down to the bottom of the plate against time. And what I want to do here is to introduce the bizarre nomenclature that the field uses, which is state 2, state 3, state 4, and just kind of explain where it comes from and try and make it seem less just magic and more logical. So in the 1950s, Chance and Williams did this experiment first, probably using manometers, where they were measuring the oxygen consumption rate of isolated mitochondria. And they discovered that when they made various manipulations, adding substrates, adding ADP, adding various inhibitors, they could change the rate of oxygen consumption. They could change the slope of this relationship of oxygen tension against time. And they had a standard experiment they ran, and they just called the different rates, state 1, state 2, state 3, state 4, state 5, state 6. And because they were towering dominant figures in the field, that nomenclature then was adopted by everybody else. So now we talk about state 3 respiration or state 4 respiration, and it all refers back to these original experiments done by Chance and Williams. So the way they set up their experiment was they would add some mitochondria to a solution in a closed vessel, measure the oxygen tension, and nothing much happens. And so that was state 1. And then in their experiment, they added ADP, and the mitochondria were able to respire rather sluggishly on their endogenous substrates. It turns out that it's more useful to add substrates, so state 2 changed in meaning from the way that Chance and Williams set it up to substrate alone. So these days, if you add, say, succinate to start to drive electron transport, then we call that state 2. And it turns out that state 2 is very much like state 4, so sometimes we're a bit imprecise and we also call it state 4, although technically it's not really state 4. And then the interesting change happens when you add ADP. So you ask the mitochondria to convert that ADP into ATP, so you've changed the forces across the ATP synthase. So as David explained, that change in the forces then changes the proton-motor force through protons flowing back through the ATP synthase. And that change in proton-motor force changes the forces across the electron transport chain. So the delta EH goes out of equilibrium with the delta P. So the electron transport chain is moved away from its equilibrium value, so it goes faster. So you add ADP, the mitochondria start to turn it into ATP, and they go faster. The respiration increases into state 3. And the state 3 is the shorthand that we always use for that rate of respiration, which is not limited by ADP supply. There's plenty of substrate, there's plenty of ADP, the mitochondria are running the whole of oxidative phosphorylation as fast as they can go. So state 3 is a very useful description of the capacity of the whole system. And then at some point the ADP is exhausted. The affinity of the adenine nucleotide carrier for ADP is very high. So the ADP is either there or it's gone. There's very little in between. So there's a very sharp transition between, yes, there's ADP around and no, there isn't. And then it drops below the Km and you switch into this lower rate, the state 4 rate. So what's happening here is the ADP is gone, so the phosphorylation potential is now risen to near its maximum value. Now the ATP synthase is able to come to equilibrium where the proton-motor force and the delta GP come to their equilibrium connected by the proton movements and the stoichiometry of the proton movements. So the proton-motor force rises to hit the maximum value, and that then throws the equilibrium across the respiratory complexes back towards their equilibrium. So they slow down as they move closer to equilibrium and eventually run down to their lowest rate. And you just get a residual rate, which is caused by the proton leak rate across the mitochondria, just allowing the system to trickle electrons down the electron transport chain and just turn over. So the state 4 rate then is a very useful rate to see because it tells you about that basal proton leak across the mitochondrial membrane. And then if you add uncoupler, you can get rid of the proton motive force by allowing the protons to flow across the membrane. There's now no constraint on the electron transport chain, and it runs at the uncoupled rate, which wasn't called this by Johnson Williams, but subsequently people called state 3U for uncoupler, the uncoupled rate. And then they had some other states which nobody ever uses. State 5 is this rate when everything's finished, when the oxygen's run out. State 6 is a particular condition. And I talked about state 3U, which is the uncoupled rate, but there's also state 4O, which is the oligomycin inhibited rate. So instead of waiting for the ADP to run out to get state 4, you can just inhibit the ATP synthase with oligomycin, and you get about the state 4 rate. And so the state 4O is the oligomycin inhibited rate, which sometimes is easier to get. And then while these changes in respiration rate are going on, you see the corresponding changes in one of the forces, the proton motive force, here measured as proton motive force in some of David's earlier work, measured using radioactive probes and then constructed as a line. These days we do it with fluorescent probes. So when you add the succinate, or before you add the succinate, there's very little proton pumping, so very low proton motive force, so we set that to 0. When you add the succinate, you can now pump protons, so the proton motive force rises to approaching 180 millivolts, something like that. When you add the ADP, you throw the system out of equilibrium, so the proton motive force drops as it tries to drive the ATP-ADP ratio back to its original value. It only drops by 20 or 30 millivolts, and then it's more or less stable, slowly rising as the phosphorylation potential increases until you hit state 4, and there's an offset in time, which is just setting up the figure incorrectly. These should match in time. So as you go back into the state 4, the proton motive force rises back to the original value it had in state 2. And then when you add uncoupler, it dives, and it again should dive instantaneously to 0. This is a reflection of the measuring artifacts. So it's a dive to 0, and it hits 0 very quickly, and the respiratory chain runs at its maximum rate. So these are the rate changes that occur. They're all these rapid within seconds changes, and they're entirely controlled by the thermodynamic forces within the system. So here what you're doing is when you add the succinate, you're changing the delta EH by adding an excess of succinate with no fumarate present. So you drive the reducing potential very high. So you drive the electrons into the electron transport chain down to oxygen, and then measured by the oxygen disappearance at the end by the oxygen electrode. And then when you add the ADP, you're throwing the phosphorylation potential out of equilibrium by having an effectively infinite supply of ADP. So the phosphorylation potential drops to near 0. And then as the mitochondria convert it back into ATP, eventually it's all ATP and you go back to equilibrium, and the rates follow these changes in potential. And when you add the uncoupler, you're collapsing one of the forces. So the rates run because they're now way out of equilibrium, and they would run forever, but eventually the oxygen runs out. So everything stops. And it turns out that the ratio of the state 3 rate to the state 4 rate is a very useful index of how good your mitochondria are. So the things that determine the state 3 rate need to be good in order to get a good high state 3 rate. And the things that determine the state 4 rate need to be very small in order to get a very good state 4 rate. So if you divide the state 3 rate by the state 4 rate, you get a number called the respiratory control ratio, or the respiratory coupling ratio. And the bigger that number is, the better. It tells you your mitochondrial preparation is really good. So I just want to examine what controls those rates and what controls that respiratory control ratio, which is the classic determinant of having good quality mitochondria. So the respiratory control ratio then is the ratio of the state 3 to the state 4, or alternatively the uncoupled rate to the oligomycin inhibited rate, state 3U to state 4O. And I'll show why you might prefer this one over this one in just a second. So what determines the respiratory control ratio? Well, it depends on the value of the state 3 rate and the state 4 rate. And the state 3 rate is determined by the kinetics of the phosphorylation system. So the kinetics of the adenine nucleotide translocase and the phosphate carrier that let the ADP and the phosphate into the mitochondria, by the kinetics of the ATP synthase, and then by a bunch of other parameters like the pH in the matrix or the magnesium in the matrix, and various other things. So the phosphorylation system kinetics. But it also depends on the substrate oxidation kinetics, and they have about equal control over that state 3 rate. And I'll explain in a while, maybe in the next lecture, how I know that. The state 4 rate is determined primarily by the proton leak rate. Also, if you use things like muscle mitochondria, it's controlled by the ATPase contamination. So if you make some ATP and there are ATPases in the prep, then those ATPases hydrolyze it again back to ADP. So it takes you much longer to get to the state 4, or you never get there because there's always some ADP coming back into the system. So the proton leak and the ATPase contamination determine that state 4. If you add oligomycin, you don't care if there's ADP being put back into the system because you're not phosphorylating it. You're using the uncoupler instead to modify the proton-motor force. So the state 4 rate doesn't care about the ATPase contamination. The state 4 rate itself does. And that's one of the reasons for preferring the state 4.0 over the state 4, or the state 4 over the state 4.0. So if you're interested in how pure is your prep, state 4 is better. If you're interested in how much are your mitochondria beaten up, then the state 4.0 ratio is better because it's independent of, are they also dirty and contaminated by ATPases from the cell. Same with the state 3U rate. It's determined in the presence of uncoupler only by the electron transport chain and the substrate uptake capacity. It's not controlled by the ATP synthase. So if your interest is in the electron transport chain and not the ATP synthase, you don't care whether this part of the system is working well or not. You only care about the electron transport chain. So you prefer the state 3U rate. So state 3U over state 4.0 tells you about a specific subset, which is how good is the electron transport chain working and how leaky is the membrane. Whereas the state 3 over state 4 tells you a more global picture of how clean is your prep and how is the ATP synthase machinery also working. So if you make mitochondria, the first thing you do is you measure the respiratory control ratio to see if it's any good. And if it's 1, in other words, if you can't stimulate the rate with ADP, then either you've screwed up your machinery for making ATP, or you've screwed up the electron transport chain, or you've made the membrane permeable to protons. And those are all bad things. So you go back and you improve your preparation until you get coupling back and the respiratory control ratio climbs above 1. And it depends on the tissue because that determines the rate constants in the system. It depends on the respiratory substrate because, again, there are rate constants which are different between the succinate or the glutamate and malate that you would use. And it depends on the thermodynamic properties of those substrates. It depends on the respiratory substrates that you choose to use. But for something like mouse liver oxidizing succinate, you need to get a number above 3, and 4 to 5 is a good preparation. If you use rat muscle mitochondria oxidizing glycerylphosphate, you'll get different numbers. So depending on the tissue and the substrate, you'll get different numbers. A ratio of 4 to 5 is good for mouse liver. If you get a ratio of 1, I can tell that you're not making mitochondria that are any good. But the inverse is also true. If you get a ratio of 50, then I know you don't know how to do your experiments because the kinetics of the mitochondria are kind of the same in every lab in the world. And they determine, or partially they determine what this ratio is. And from the given kinetics, you can't get numbers more than about 10 for mouse liver oxidizing succinate, whatever you do. So if you get an answer of 50, it's because your oxygen electrode doesn't work correctly, or you've wrongly measured your rates in some way using the seahorse. So it's very handy to measure the respiratory control ratios. They tell you 2 things. They tell you how good is your preparation of mitochondria, and also when you peer over somebody else's shoulder, they tell you how well are they using their equipment to measure their respiration. So I've got
Professor Brand, I have a question here. So when you are looking at these values, how do you say that it's a fault of a machine or a fault of your sample preparation when these values go beyond certain level or something?
Yeah, so empirically you don't know to start with. So if you work on your own in a lab, you make some mitochondria, you set up a seahorse or an oxygen electrode, and your respiratory control ratio is 1. In other words, the ADP doesn't stimulate the rate. You don't know if it's because you don't know how to use the seahorse or you don't know how to make mitochondria. So what we normally recommend is you find somebody that does know one of those two things. So you get some mitochondria from a lab that knows how to make them, and you run them and show that you can see something. Or you use a machine that somebody else has set up and is working and demonstrate that your prep is able to give something. So normally you break it into the two variables and test them independently. If you can't do that, it's harder because you have to check all the variables until something starts to work. And then you can try and work out where the problem lay. Partly you can tell just by the rates. So there are plenty of published values for what the absolute rates should be. And if your rates are 10% of what everybody else sees, that probably means you've just wrecked your mitochondria. So the absolute rates also tell you what's going on.
Thank you.
Okay, so in the remaining 10 minutes, or I may overrun a little bit, I want to talk about how do I know what's controlling these rates? And how can you actually calculate what's rate controlling over different aspects of the respiratory control experiment. So here's the simplified view of oxidative phosphorylation using succinated substrate that David went through. So we can just call it an electrical circuit where we have an electrical flow, we have a proton flow, and we have a flow back through the ATP synthase. But for the purposes of the discussion, I'm going to simplify it even further. So we can group everything to do with the oxidation of the succinate and the electron transport chain into a single thing, which we can call substrate oxidation, a single module. So there's a module in mitochondria which takes the substrate, runs the electrons down the electron transport chain, and pumps protons across the membrane. That sets up a protomotor force, and then there are two modules which are able to consume it. One is the leak of the protons back across the membrane, and the other is the driving of those protons through the ATP synthase to make ATP from ADP and phosphate. So that's the phosphorylation system and the proton leak. And sometimes we can combine these together and call them protomotor force consumers, and sometimes it's more helpful to keep them separate so we can see what the leak is doing and we can see what the ATP synthase apparatus is doing. So I can redraw that diagram now as a simpler system where we simply have a supply reaction, the substrate oxidation, setting up an intermediate, the protomotor force, and that then drives a demand, which is the proton leak and the ATP turnover. And we have a system which has got a boundary to it. And when we're working with isolated mitochondria, that boundary roughly corresponds to the mitochondrial inner membrane. When we're working with cells, it often roughly corresponds to the cell membrane. And sometimes if we're working with human beings, it might correspond to the cell membrane in the liver, even though your experimental system is a human being and you're poking them in different ways to try and see what happens to their respiration. So this goes back to define the limits and the extent of your system, because we're interested in control, and you have to define your system before you can meaningfully talk about control. And mostly I'm talking the time domain of seconds or minutes, because we're doing the experiment in a seahorse or some other machine. So we're talking about that very rapid time domain. So just think philosophically about such a supply-demand system. So we have a supply reaction making an intermediate, and we have a demand reaction which is consuming it. And let's set it into an infinite universe where the substrate is fixed and never runs out. The product that we make dilutes into that universe and never builds up. So we have a supply which is making an intermediate and a demand which uses it. And we can now describe the kinetics of that system. So let's just plot the rate of the substrate as a function of the intermediate. So what would you expect to see? Well, you'd expect to see that when the intermediate gets bigger and bigger, the supply should go slower and slower. That's the general reaction. It doesn't have to be that way. But in general, if you're working against a great big product of the supply reaction, then the supply is going to be product inhibited. It's going to go slower and slower. So we can draw a line for the kinetics of the substrate supply reaction. As the intermediate gets bigger, the supply in general gets smaller. And I've chosen a particular shape of curve because that corresponds to what actually happens in mitochondria. If we look at the demand part of the system, so forget the substrate supply, just look at how the intermediate affects the demand reaction, you'd now expect the opposite, that as the intermediate gets bigger and bigger, that's a force which is driving to the constants in the demand kinetics, driving the flux. So you'd expect that you'd get a faster and faster rate. And in irreversible thermodynamics, you get a linear faster rate. So we get some sort of increase in rate as the intermediate increases in concentration. And again, I've drawn a line which corresponds to the real proton leak kinetics in mitochondria. But in principle, it's just some line that goes up as the intermediate increases. So now let's put those two halves of the system together and say, if we have an infinite supply of substrate and a supply reaction with some kinetics or other, and an infinite sink for the product and a demand with some kinetics or other, what would be the value of the intermediate in the steady state? And because there's a unique relationship of the intermediate concentration and the supply, and another unique relationship or set of relationships of the demand reaction and the supply, at some point, in the intermediate, at some intermediate concentration, these two will go at the same rate. And in terms of our kinetic plot, that's when the two curves cross. So if we dump this system into reality and let it run, it will run until the rate of demand and the rate of supply are equal, and the intermediate will evolve until it hits the appropriate concentration to ensure that that happens. And if that's not obvious, think about what would happen if we intervene into the system and artificially lower the concentration of the intermediate. So we pull it down with some third reaction. Well, what happens is now the supply will go faster because it's on its kinetic curve up here, and the demand will slow down because it's on its kinetic curve down here. So supply will go faster, demand will go lower, so the intermediate will start to build up, and you'll evolve along these two curves until you reach this point where they're at the same rate. And then you'll hit the steady state, and the system will be stable and won't change in time and until infinity. Or conversely, if we just dump a bit of the intermediate into the system, so it's now too high, that will inhibit the supply because there's more intermediate than it wants to make, so it'll slow down. It'll increase the demand because there's more intermediate there, drives a higher demand. So the demand will go faster. It'll consume the intermediate. The supply will make less of the intermediate, and gradually the intermediate will get used up until you go back to this steady state again. So this is a stable equilibrium set by the rate constants in supply and demand, and it will always evolve to the same value of the intermediate set by the kinetics of these two supply and demand reactions. And it's infinitely stable. As long as you don't change the kinetics, the system will run until the end of time at that intermediate concentration and at that rate set by these kinetics. So the force, the intermediate here, is determining the flux through this system, and the kinetics, the K values, are what actually determines which particular value it ends up at in the longer term. Moment by moment, it's only the forces. In the bigger picture, it's the kinetics and the forces that determine where we end up. So now let's do a thought experiment. Let's add a bit more of the demand reaction. So let's say it's two enzymes in a tube, we just sprinkle in some more of the demand enzyme. So now we switch to a new demand kinetics, where the demand reaction goes faster at any given intermediate concentration. So if we were to double the amount of this catalyst, the rate would be twice as fast at a fixed intermediate concentration. So we end up with another line displaced twofold from the first one. But what really happens is it now evolves along the supply line to a new steady state, where we're still on the same supply line because we haven't touched the supply kinetics. But because we've changed the demand kinetics, we've changed the steady state to a different one. So that's a really important concept. So I'll say it again. If you increase the kinetics, let's say you change the rate constant in the demand block, we just add more of the demand enzyme, if it's an enzyme, you end up on a different demand curve, but you're on the same supply curve. And you'll end up in this steady state where somewhere on the supply curve, the lines will cross, so you'll get another intermediate level, but on the original supply curve kinetic line. So you can expand that idea and just titrate the demand. So let's progressively increase it. And as you progressively increase it, you evolve through these different steady states along a curve that maps out the kinetics of the substrate supply. So what you can actually do is to play around with the demand kinetics, measure the steady state intermediate level, plot it out, and that gives you the kinetic response of the substrate to the intermediate. And we're going to use that to look at isolated mitochondria and measure the kinetics of the substrate oxidation system to the proton motive force. And as I'll show you at the end, you can also do that in intact cells or in intact organs in animals and measure the kinetics of the substrate oxidation reaction in situ just by simple titration. So if we want to know the kinetics of the supply reaction, we just change the demand reaction. If the substrate oxidation is the supply reaction, then the manipulation we make is we change the kinetics of the demand, which is the proton leak and ATP turnover. So we can just increase the ATP demand or the proton leak demand by uncoupling. We can increase the proton leak, and we can titrate the kinetics of substrate oxidation by altering the proton leak. And that gives us that kinetic curve we just went through. So we can change this. So you can change this by adding a coupler to work out the kinetics of this. Same thing now applies if we want to work out the kinetics of the demand reaction. We can inhibit the supply. We can add an inhibitor of the electron transport chain, for example, if we look at mitochondria. We'll now have a different kinetic curve for the supply reaction. It'll go more slowly at any given intermediate concentration, and it'll evolve to a new point on the demand line. And then we just repeat our titration to map out the demand line and see what that looks like. So now we're asking, how can we measure the kinetics of this demand block? Well, the answer is we just change the supply block and measure the intermediate and the fluxes. So if our demand block is the proton leak, which we can ensure by just adding oligomycin to inhibit the ATP turnover block. Then what we do is we alter the kinetics of the substrate oxidation. We just titrate state 4O with malonate to progressively inhibit the flow into the system, measure the proton motive force, measure the flux through the whole system with a substrate oxidation measurer, the respiratory chain, the oxygen consumption rate, and that tells us the kinetics of the proton leak reaction. So by a simple titration, state 4, we can measure the kinetics of the proton leak in a complicated system. We can measure the conductance of the mitochondrial inner membrane. And those were curves that David showed you earlier on, and we're going to come back to 2 or 3 times during this lecture. And if we want to measure the kinetics of the ATP synthesis block, then we leave out the oligomycin. We just let ATP turnover run. So we put them into state 3. And now what's running in the demand block is both the ATP consumption and the proton leak. So we see the sum of the two. We titrate out with an inhibitor of the electron transport chain to get the curve of the sum of the two. And then we subtract off the proton leak to get the difference between these two lines as the kinetics of the ATP turnover system. So by simple titrations, we can measure the kinetics of all 3 modules of this simplified system of oxidative phosphorylation. We just measure the proton motive force, we do the appropriate titrations of substrate and demand, we plot out how the rates change as we titrate. And that gives us the kinetic responses to these forces of the three components in the system. And that turns out to be really powerful in terms of understanding how control is exerted and how regulation is concerted in these systems. So I've run over time. I think I'm going to stop here for the lecture, and we'll take the break and I'll pick it up afterwards. But where we get to then is that this is now real data taken from our historical literature, looking at isolated mitochondria where we've done what I've just described. So we take isolated mitochondria, we put them into state 4 by adding oligomycin. So we put them into state 4.0. We measure the proton motive force as the membrane potential with nigericin present to make sure there's no delta pH, and the whole of the proton motive force is expressed as membrane potential. We measure the respiration rate with an oxygen electrode in those days, and we plot the oxygen consumption rate against the proton motive force. And then we titrate out either by adding more uncoupler, and that gives us the kinetics of the substrate oxidation block. So this is the kinetics of the electron transport chain and the substrate uptake and all of the other ancillary reactions that are part of substrate oxidation. That tells us how that curve looks. And that was one of the curves that David showed you when we were talking about uncoupling and how you drive the substrate oxidation, and how near state 3 you're in this critical point where suddenly everything collapses if you add any more uncoupler, and the proton motive force collapses completely, and that leaves you in doo-doo, is his expression. If you titrate state 4.0 with instead an electron transport chain inhibitor, then you get the kinetics of the proton loop. And that's what tells you about the proton conductance of the inner membrane, and you can use that to look at the activity of uncoupling proteins, for example, which David and I both will talk about later in the course. So by a malonate titration of succinate oxidation in isolated mitochondria, you can measure the kinetics of the proton leak in those mitochondria, even though you can't directly measure those fluxes across the microscopic membrane. And if you push the mitochondria into state 3 by adding an excess of ADP or a system that turns over the ADP, then you can titrate out the ADP with the ADP-driven phosphorylation reaction, the state 3 respiration rate. You can titrate it out with inhibitors of electron transport to get the kinetic response of the whole system, and then the difference between these two curves is the kinetics of the ATP turnover reactions. So all of the forces in this dynamic system are driving the fluxes. When you come in the morning, you've determined the kinetics. So your kinetics are all constant. And so all of the rate changes that are going on during this state 3 to state 4 transition are driven by these changes in forces. And we can understand something about kinetics by looking at those forces. So these curves map out the kinetics. And if you're interested in a genetic change in some protein which is having bioenergetic effects, the way it will manifest in this seahorse experiment or in this oxygen electrode experiment will be to change the kinetics of one of these 3 blocks. It has to change one of those 3 blocks because when we defined the system, everything was included in one of those modules. By definition, there's nothing left out. Therefore, anything that you change that affects oxidative phosphorylation will be in one of these 3 blocks. And if it affects OXPHOS, then it will change the plot. Otherwise, it's not changing OXPHOS. And your experiment is no, it didn't do anything. So if it does something, it'll change one of these lines, at least one of these lines. So this is a really powerful system to understand how your drug treatment or your genetic modification or your evolutionary change caused by a million years of evolution, how it altered oxidative phosphorylation and changed its function. The mechanistic way you get at that is you come back to this experiment, you run it and you ask, which of these lines changed? And that tells you which module changed. And then if it's the proton leak, you can then ask the subsidiary question is, why did the proton leak change? Or if it's the substrate oxidation that was affected, you could then break it down and say, which bit of substrate oxidation changed? Was it complex 1 kinetics? Was it the uptake of the substrate into the mitochondria? Which bit changed? And you can define the question down to a molecular level, and then eventually down to an amino acid substitution level or an active site inhibition level to really determine what was the effect of your change, and therefore what's the mechanism of your pharmacology or of your interesting biology that you're trying to understand. Okay, so I will stop there. And we'll take a break for lunch. And then I'll pick up again with the remains of that lecture and the next lecture after lunch, and that will then lead into the practical session, the data handling session we have later on, where instead of listening, you're going to be doing the thinking and the talking and interpreting what's going on in terms of these ways of thinking that we've been presenting. So if I've got my timings right, we're now going to break for an hour. I'm going to go away and get a sandwich and then come back and see what breakout room I'm in and chat to who's ever in there. And so let me pick up where I left it. So this was originally one lecture and it has been broken into two, and I got the break point slightly wrong in the timing, but I've just pasted across the odd slides into this one so I can pick up the story and continue. So we're trying to address what is it that controls the rate of electron flow and the rate of ATP synthesis in oxidative phosphorylation, and how can we use these force flux relationships, looking at the displacement of equilibrium of the forces in these short time course experiments to understand the underlying changes in the kinetics, which might be our question of interest, which is how did my treatment change the machinery of oxidative phosphorylation? So as I said, we can simplify the system into this 3-module system of substrate oxidation, proton leak, and ATP turnover, or re-simplify that to a supply intermediate demand system in order to analyze it.
I don't think we can see the slides.
Okay. I will restart the share. I don't understand what I'm doing wrong here.
I think you need to be in present mode.
Yeah, I was in presenter mode.
I think this is the Mac problem that I was having earlier, where it doesn't always track to presenter mode. Sometimes it just stays on the PowerPoint, but now it looks correct.
You got it now?
Try advancing a slide.
Is it advancing?
Looks good.
Okay. So this is the simplified system in 3 modules or 2 modules that I just referred to. And this is the experiment that we're basing it all back to trying to explain, which is the respiratory control experiment, where we measure the rates of respiration in state 2, state 3, state 4. And we are trying to understand why the ratio of state 3 to state 4 is a really sensitive way of looking at the quality of your mitochondria. And by inference, a really good way to see if the kinetics of any part of the system has changed before you do a deeper dive into what that part might be. And I just showed you at the end of the last lecture the modular kinetics of the system, where we start here in state 4.0 and we titrate with uncouplers to get the kinetics of the substrate oxidation module. We titrate with an inhibitor of electron flow to get the kinetics of the proton leak module, or we can put ourselves into state 3 and titrate out the electron transport chain to get the kinetics of the combined consumers. And then by difference, we can work out the kinetics of the ATP turnover system and the kinetics of the proton leak separately. And then the point I was trying to make was that this is a really sensitive system for seeing small changes in the kinetics of any part of the system of oxidative phosphorylation. So the system by definition contains everything, because we've modularized it to say everything in this part is in this module, etc. So everything is in there, and therefore any change that is meaningful will show up as a change in the kinetics of one of these modules. And this is the demonstration of that. So we take our isolated mitochondria and we repeat the experiment with a deliberate slight inhibition of the electron transport chain. So in this case, we titrated mixothiazole to as low as we could go and still see a signal that changed within the noise. And this is the result of the experiment. So when we add a little bit of mixothiazole, which is an inhibitor of complex 3 electron flow, when we add a little bit of mixothiazole to the standard condition, our new state 4.0 turns out here instead of here. And now when we titrate with uncoupler, we see a different curve. Whereas when we start from here and titrate with malonate, we get an overlaying curve, which is indistinguishable from the original one. And when we put it into state 3 and titrate again, we get indistinguishable curves. So we can say from this two things. One is that mixothiazole has had its effect in this system with a very small change in the proton-emitting force and the respiration rate caused by a change in the kinetics of the substrate oxidation system, which of course is what we know it does because we added an inhibitor of the electron transport chain. But we can also make the strong inverse inference, and that is that we haven't changed the kinetics of any other part of the system. So the kinetics of the proton leak are unchanged. So mixothiazole demonstrably does nothing to the kinetics of the proton leak. Mixothiazole demonstrably does nothing to the kinetics of the ATP turnover system. And for mixothiazole, which is a well-examined, well-understood inhibitor, that's the expected result. But imagine you were using instead some unknown compound, which was known to affect the function of mitochondria, but you didn't really know where it is. Then this would be a way of finding out where it was working. Ricky, are you on? Ricky?
Yes.
Can you email Nick and tell him I'm not joining his meeting, I'm otherwise engaged?
I shall.
Thank you.
Sure.
So if you didn't know what your inhibitor was, you'd be able to say unambiguously from this experiment, whatever I've done to this system has changed the kinetics of the electron transport chain and done nothing else significant in oxidative phosphorylation, at least under the conditions that you did your test experiment under. And that could be very powerful for an unknown gene, expression change, an unknown disease, an unknown pharmacological agent, an unknown poison. And then just to illustrate why it's more informative to measure both the fluxes, the respiration rate, and the forces, the proton-emitting force, than to just measure one or the other. This is a hypothetical, I just constructed it by drawing the line of what would happen if I added a small amount of uncoupler to the system. So if you add a small amount of uncoupler, the proton leak kinetic curve should move from this to something further up here. It goes faster at any given driving force. And you would end up at a new steady state here with a slightly lower PMF and a slightly faster respiration rate. And you would see the effect of just uncoupling. But imagine that you were using some unknown compound which both inhibited the electron transport chain slightly and uncoupled slightly. Those can be quite tricky to diagnose because they're doing two different things. If you do this full plot of forces and fluxes, so this is now a hypothetical where it does this to the substrate oxidation response, it does this to the proton leak response, and you end up in a new state 4, which is not really distinguishable in respiration rate from the original one, and a small change in potential. When you do these kinetic plots, it's still very obvious that it's doing two different things. And in terms of the respiration rate, they're canceling out. So one of them is increasing the respiration rate. That's the uncoupling effect. And the other one is lowering the respiration rate, the inhibition effect. And the net result, if I'd drawn it right, would be no change in respiration at all. So if you're using just an oxygen electrode or just a seahorse, you would completely miss this effect. You would say, my treatment did nothing. But in fact, what it's doing is two complicated things which cancel each other out in respiration. And you would only see it if you measured the membrane potential, which in this example drops by 5 or 10 millivolts. And if you do both, you find out immediately that it's having primary effects on both of these parts of the system. So it's a multipotent compound. And in fact, that's really very common with mitochondrial poisons. So things that bind to the mitochondria and dissolve in the mitochondrial membrane, while being weak inhibitors of the electron transport chain, often also uncouple. So it's a classic finding that complex 1 inhibitors will do exactly this. They'll both inhibit and uncouple, with net not all that much change in respiration until you do this sort of plot and then disentangle what's going on. So this reiterates the point that David made, measuring both the fluxes and the forces, measuring both the respiration rate with the ammeter and the protomotive force with the voltmeter is better and more informative than just measuring one. Obviously, the reason we only measure one in most experiments is it's easier just to measure one thing than to measure two. So that's where you start, but you lose information by not measuring all the relevant parameters. And I use parameters very carefully in that context, because that allows me to extend what's going on here to really show the power of knowing how these kinetics are behaving. So what we're doing is we're teasing out both the K value in that original equation, which determines rates, J equals K times a delta G component. So we're measuring the K component by looking at these titration curves and seeing how they're shifting. And we're measuring the forces, the protomotive force at the same time, to understand how the forces are changing. And it turns out that if you know both the kinetics and the forces, you completely understand the system. You don't often hear biologists say that, but at the level of simplification caused by the modularization, it's a very simple system and you can completely understand its behavior. So using this sort of approach, you can completely describe the behavior of this system at that level. Obviously, you don't know all the molecular detail, so you would go back in to find out those bits that you don't understand. And the way into completely understanding it is control analysis. So I won't spend 5 minutes just giving you a brief outline of control analysis, because it's a very powerful way to think about these biological systems. And even if you don't master all the different equations and the different theorems of control analysis, just using it as a way of thinking about what's going on can be really extraordinarily helpful and resolve a whole set of problems that otherwise seem insurmountable. So control analysis is an algebraic type analysis. So it shares with algebra the idea that it's not wrong or right. Algebra is not wrong, it's just a way of manipulating relationships. And it might be inappropriate to use algebra when you're trying to work out the bill at your supermarket, but it wouldn't be a mathematically inappropriate or false way of doing things. In the same way, control analysis is a way of manipulating underlying theorems about how the universe and mathematics work. So it's not wrong or right, it's just a tool. But the way you apply it could be inappropriate in any particular condition. And control analysis is really remarkably simple conceptually. So we define a system, and as I was talking about in the first lecture, defining your system is really important, because if you define it differently, the answers are different. So in a defined system, what control analysis says is that there's a bunch of things which you as the experimenter have control over, and we'll call those parameters. So the parameters might be the pH that you decide to do the experiment at, or the salt concentration that you use, or the source of mitochondria that you put into a pot, or the cell line that you grow and how long you've grown it and under what conditions you've grown it. And once you've set up the parameters in a system, the system itself then sets a bunch of other things, which are then called variables. So an example of a variable would be that steady state I was talking about, where the parameters, the kinetics of the supply and demand blocks, interact in a way which always gives the same answer, which is a particular rate of respiration and a particular protomotive force. And given those parameters of what the kinetics are, you will always get the same value of the variable. But you don't, as the experimenter, set that variable. You have no control over it, the system does that. So what the system sets is a variable, and what the experimenter sets is a parameter. So in any biological system, there's a bunch of parameters, you know, what your animal is that you're looking at, or what your salt concentration is in the medium, and a bunch of variables, which is how the system then settles down into a steady state, and what its various forces internally, what value they evolve to, and what the rates within the system evolve to. And those are set by the system given a certain starting point. And in most systems, they'll always evolve to the same answer every time you do the experiment, except for chaotic systems where there's more than one answer to the way you can solve the problem. And then what control analysis says, okay, let's make a small change in a parameter. And in strict control analysis, you make an infinitely small change because it's like a differential calculus. It's an analysis of infinitely small changes. In the real world, we make real changes and approximate to infinitely small ones. So let's make a small change in one of the parameters. For example, let's make the membrane a bit leakier to protons by adding a little bit of uncoupler. So that's a parameter change. We've changed one of the kinetic constants in the system. In this case, the kinetic constant that tells you how fast protons cross the membrane at a given driving force, protomotive force. And then control analysis says, okay, if we make let's say a 10% change in a parameter, what happens to a variable? So the variable would be the respiration rate in this example. So if we change the proton leak by 10%, what happens to the respiration rate? And if the respiration rate changes by 10%, then you say this parameter is rate controlling. It's the rate controlling parameter for this variable. In the real world, they never change in a one-to-one ratio. So in the real world, the control coefficients, which is the ratio of the change in the variable over the change in the parameter, is always less than 1. And so nothing is ever completely rate controlling over anything else. So you make a small change in the amount of uncoupler and you measure the change in respiration rate. And by how much the respiration rate changes when you change the parameter, you can say how sensitive is the state 4 respiration rate to the proton leak of the mitochondrial membrane. And that's what we want to get back to in order to understand the respiratory control ratio experiment, is what's that state 4 rate sensitive to, and therefore will it change under conditions of a disease where the proton leak has changed or not. So flux control coefficients just quantify this idea. So something that's completely rate limiting has a control coefficient of 1. Something that has no effect on the variable ends up with a control coefficient of 0. And in the real world, most of the time you move between 0 and 1. The control is somewhere between 0 control and full control by any step over any variable. So I can illustrate that going back to this diagram. So here's the flux diagram where the system has evolved to this state 4 steady state rate and steady state value of the protomotive force. And we can now do our small change in the parameter. We can add enough uncoupler. In this case, I tried to draw it to make a 30% change in the rate of the proton leak. So we added enough uncoupler to displace this curve upwards by 30%. I'm not sure I drew it accurately, but that's what I'm using as my example. So when we do that, what we find is that the steady state the system has evolved to now doesn't go up by the 30% that we imposed by adding the uncoupler, but instead it collapses back down onto the supply curve and it goes up less than 30%. Does that make sense? So we make a 30% change in one of the kinetics, but the steady state doesn't change by 30%, it only changes by something less. And in this case, let's say it changed by 20%. So we didn't get the full respiration rate change we imposed because the substrate supply also changed its kinetics and tried to work against the change that we'd made. So the control coefficient then is just the fractional change in the respiration rate, which is the variable, divided by the fractional change in the parameter, which is the 30% we made in the proton leak. So it's the 20% change over the 30% change that we imposed, which is about 2/3, 0.7.
Martin, how would you know that you imposed a 30% change and only got a 20% change if what you measure is just the 20%?
So we measure the kinetics. So the 30% change means, although I've drawn it badly in the diagram, that this point on the same vertical is exactly 30% higher than this point. So the whole curve has shifted up by 30%. But the place that you evolve to doesn't shift up by 30% because you travel along this supply line. You don't travel along the vertical. So because this has a slope, you get less than a 30% response of the variable, which is the respiration rate. So you know that you've changed the parameter by 30% because you measure it. And then you can measure the change in the variable, which is less than 30%. And the reason is this line is not a vertical, it's got a slope. And if it was horizontal, then the rate would collapse, the intermediate would collapse to 0. And the rate would not change at all. Puzzled looks. So I'm getting on my screen here. And then let's just make the opposite change, just to make another point. So let's make a change in the kinetics of the supply module. So let's increase the electron transport chain. Let's add some more succinate to a system which is limited by the amount of succinate. And we'll arrange it so that, again, we get a 30% increase in the kinetics of the supply module. So there's an offset here by 30% if I'd drawn it correctly. And again, where we actually end up is not a 30% change. We end up with a 9% change because we travel up and down this demand curve, not up and down the vertical. So here the control coefficient is 9% of the 30%, which is about 0.3, which is the other part of the sum of 1. So the control coefficients always sum to 1. The control over anything is always 1 by all the bits of the system added together. And in this case, in our simple system of only 2 components, that 1 is divided 70% into the substrate supply, into the proton leak, and 30% into the substrate supply. So by doing these kinetic analyses, which are really easy to do, you can do them in an afternoon on an electrode set up appropriately, plot out the curves, you can measure the control coefficients, and you can say unambiguously how much each of those modules is controlling the rate of respiration. And it's an experimental measurement, so it's a fact, as long as you've measured things without making errors. It's a fact that in this system, under these conditions, the control by the substrate oxidation in this system is 9%, it's a 9% change of 0.3, a 30% control, 0.3 control coefficient. So I modeled roughly what really goes on in state 4.0 in isolated mitochondria. The flux control coefficient of the proton leak over respiration is about 0.7. It varies a bit, 0.7, 0.8, 0.9, depending on the conditions. If you have better mitochondria, that goes up. If you have worse mitochondria, it goes down. And the remainder of the control is in the rest of the system, which in this case is substrate oxidation. So 0.3 in substrate oxidation, 0.7 in respiration. And then what that means is if I was to change the proton leak by a certain increment, and I was to change the substrate oxidation by the same increment, they would have different effects on the respiration rate. Because one of them is multiplied by a control of 0.7, so I get 70% of that effect if I change the proton leak. But it's only multiplied by 0.3 for substrate oxidation, and I'd only get 30% of that change for substrate oxidation. So maybe you can see where this is going. If you do some unknown where you have a pathology or a disease or a genetic change, how much that change affects the rate depends on which rate you're looking at and how much control the actual target of your treatment has over that particular rate or that particular variable. So these considerations lead you to design experiments in particular ways so that you have the maximum control coefficient exerted by the thing you care about over the thing that you're measuring. And if you measure under some other condition, you miss the effect and you get the wrong answer, or you miss the positive answer. And it turns out that control is always shared. There are no rate limiting steps in biology. And in fact, there are no rate limiting steps in chemistry, despite what your teachers may have told you. When you have a system with lots of steps in it, every single step in that system has finite control over every variable in that system. That's the nature of a network. In biology, evolution has played with it to make sure that mostly there isn't a lot of control in one step. So in biology, you tend to have quite widely shared control, unless the biology is interested in putting a lot of control in one step. So the tryptophan biosynthesis operon in E. coli would be a classic example where biology has said it's really important to put all the control on this step, so it does that. But in general, in metabolic pathways, control is widely shared. In chemistry, there's no evolution at work. So often there, the kinetic parameters are just completely mismatched. And one step will have 99.999% of the control, and the other step will have the residual fraction of a percent. So in chemistry, it's more often to find things, more often the case that you find things that are quite close or even very close to fully rate limiting, but they're never rate limiting completely if you do the analysis at enough precision. And that then has the important knock-on implication that if every step in the system exerts some control, then where you set the boundary of the system changes the flux control coefficient of any particular step. Okay, I'll say it again. So your respiration in your muscle mitochondria, when I ask you to jump up and down, the proton leak and the electron transport chain in your muscle has some control over that process. But as I widen the boundaries of the system I'm examining, the control by your cytochrome oxidase decreases, and the control by me sitting in San Rafael increases. And in the limit, the control by me is quite high. It's limited by whether you're willing to get up and jump up and down when I ask you to, so it's never 100% control. But I can have a lot of control over your cytochrome oxidase. But then as you focus down the limits of the system without changing the enzyme itself, then gradually it picks up more control. So in isolated mitochondria, the respiratory chain will have more control than the same respiratory chain does in a cell model. And in turn, it will have more control in the cell model than it does in an animal, because you're widening the boundaries of the system. So what controls your favorite process depends on the boundaries of your system and how much it controls it. And then the control is determined by these underlying kinetics. So going back to this, if you were paying attention, it's the slopes of these lines that determine whether you get a 9% change or a 2% change or a 100% change in the variable when you change the parameter. And the slopes of these lines are the kinetics. They're the kinetic response of the flux to the intermediate. So the underlying kinetics and the relative kinetics of one process compared to another is what determines how control is distributed in a pathway. So if you measure those kinetics, as we do in these kinetic plots, you can fully understand the control, which is where my claim of fully understanding comes from. Once you've measured the kinetics, everything else is a mathematical result of those kinetics and of nothing else.
Hey, Martin?
Yeah.
If you have a curve like what you were showing, which is nonlinear, and perhaps very nonlinear, so if you're looking in your supply curve at the point where it bends, how do you know that your small change, which might result in a sort of an effect of a certain size, how do you know that you're looking at the right part of any given curve to really get an idea of control coefficients?
So the control coefficients tell you about the system as you set it up and not about anything else. So if you set it up wrong, you'll get control coefficients back, which are not appropriate for what you want to know. So what would happen here is if we instead, actually I had a thing that showed it. Oops, no, I didn't. It was in the other slide deck. But this is an example of the same set of curves. If you measure the control around here, you get some control coefficient by the leak and by the chain. If you move up here, then it's very different. Now the leak has a very different control because the slope is very shallow at that point compared to these other slopes. So the controls shift around. So I think the answer to your question is you have to define the system to ask the question you want to ask. And if you care about what controls the rate of state 3 respiration, you have to set it up in state 3. And that's going to lead on to where I'm trying to get to with this, which is that in your seahorse experiment, whether you expect your pathology or your drug treatment to change the rates depends on which rate you're looking at and how strongly the thing you care about is controlling that rate. So that eventually gets back to, should you look at the effect on the basal rate or the oligomycin inhibited rate or the uncoupled rate, because it's different. And the answer is, of course it's different, because the control exerted by your process is very different under those different conditions. So that's where I'm going. Does that answer the question?
I think it answers my question, but I'm not entirely sure I asked the right question. But I think maybe I just need to keep thinking about it.
Yeah, it makes your brain do somersaults, right? I'm trying to keep it simple, and I'm trying to show you how powerful it is once you get it. So just to finish up on that, the slopes of those lines are called elasticities, or at least once they're normalized to the initial condition. And that comes from economic theory. So this is really the theory of networks, and any network follows the same rules. So the building of refrigerators in Cleveland, Ohio, and the delivery of them to your local store to sell them to people follows all the same mathematical rules as the metabolic maps do in your muscle cells. And so the elasticity of supply and demand is a very useful concept in economics. If you have a high elasticity of supply, then demand is what determines what happens, because if the consumers demand more fridges, the factory makes more fridges. Whereas if you have a very low elasticity of supply to demand, then the price goes sky high because there are all these consumers chasing a limited number of fridges. So it explains economics, but exactly the same concepts explain bioenergetics and metabolic maps and a whole bunch of other network systems that you may come across. And then I said it already, the kinetics of the system or the elasticities of the modules determine how the control is distributed. So if you measure those kinetics or those elasticities, you can calculate out the full control structure. So here's the measurement of all of the kinetics in isolated mitochondria in a test tube under a bunch of different conditions. From this, we can measure the slopes and therefore measure all the elasticities. So we can completely solve the control structure of this system. And I can tell you under any condition exactly how strongly each of these three modules controls all of the variables in the system, the fluxes and the concentrations of the intermediate. And that's what this plot is. So here what I've done is just taken the previous data set, or nominally, it's actually built from a different data set, and measured the slopes and then calculated the control coefficients under a range of different conditions. So here's the control coefficient over the respiration rate. How strongly do each of these three parts of the system control the respiration rate? And along the bottom, it's where are we in between state 3 and state 4. So here's state 4O with oligomycin present, no phosphorylation. And then gradually we allow the system to titrate up through intermediate states up to the full state 3 maximum rate of ATP synthesis with excess ADP added. And you can see a number of things in this graph. First of all, it's completely different whether you're working in state 4 or state 3 as to who's controlling what's going on. So in state 4, most of the control is by the proton leak. In the real experimental example, it's just under 0.9. And the residue, 0.1, is in the substrate oxidation. So in state 4, if you add an inhibitor of substrate oxidation, almost nothing happens. And I showed you that with mixothiazole. There was a small change in the state 4 respiration rate, but really not very much. Whereas if you add a bit of uncoupler, you see a big effect immediately because it's got a high control. But then as you increase the rates by adding more ADP or turning over the ADP faster until you get to state 3, in state 3, changing the proton leak really doesn't make any difference. The system is going more or less as fast as it can go, limited by some components in the electron transport chain or the ATP synthase. And by changing the proton leak, you just don't change anything. So there's no change in the rate. So things that change proton leak, like uncouplers or activation of uncoupling proteins, will do nothing if you uncouple your mitochondria before you start, or if you run the mitochondria in state 3, so they're making ATP. And then in between, different parts of the system pick up control and then pass it off to other parts of the system. And it's quite complicated to work out the underlying molecular details, but it's very simple to see that from the kinetic curves.
I have a question, Martin. Do you think these are cell type specific type tracers, or do you think there's a conserved kind of mechanism like among all cell types?
So yes and no. So it turns out if you have a particular structure of your system, in this case, 1 feeding in branch and 2 feeding out branches, you will get essentially this pattern that when you increase one branch, the other branch loses control. When you change the supplies, the production branches will have if you increase the usage, then the substrate will become more limited, the substrate oxidation will become more limited. So part of the general pattern is just a function of the mathematical description of the system as 3 branches to a common intermediate. And then the details of it depend on the particular mitochondria or the particular cell. So if in a particular cell you have a different isoform of complex 4, say, which has a different kinetic response, then you'll shift these curves around within that constraint of what's possible. So at the first level of approximation, this describes any mitochondrion from any tissue, but the details will change a little bit depending on what that tissue is and what substrate you give the mitochondria. But it's a generally true statement that in state 4, the proton leak is important. It's just in some mitochondria, like brown adipose tissue mitochondria, if you don't block up the UCP, you can't get to state 4. So the proton leak isn't particularly rate controlling under those conditions. Instead, it's the electron transport chain. Okay, so this was a journey round, so I could come back to this slide and say, I know what determines the state 3 rate and the state 4 rate in my isolated mitochondria, because we did the control analysis and we measured it and we put a number on it. So the state 3 rate in particular in these mitochondria and in general in all mitochondria is determined partly by the phosphorylation system and partly by substrate oxidation. So that's this point here in the curve. This is state 3. Here's the control coefficient of the phosphorylation system. Here's the control of by the substrate oxidation system. They're about equal, and the proton leak really doesn't matter. So the state 3 rate is determined by both the phosphorylation activity and the substrate oxidation activity. And the state 4 rate is determined by the proton leak. And in these experiments, we were using state 4.0, so it's only the proton leak. And the substrate oxidation has a tiny bit of control. It was 0.1 out of the total of 1, so 10% of the control in the example I showed you. So this is the demonstration that we've done the measurements, so we know what we're talking about, that these rates are indeed controlled by these things. And then the flip of that statement is, therefore, if you change those things will or will not change the rate in your experimental system. Going back to going back to this graph here, if I look in state 4, this rate would be very sensitive to uncouplers. So if you have something that you suspect is uncoupling, measure its effect on the basal mitochondrial state 2 or state 4 rate. because that's where it's going to make the biggest change. And you're going to have a very sensitive measure. But your uncoupling is not going to show up in state 3. So don't look for uncouplers in state 3. It's the wrong experiment to do. Conversely, if you have an inhibitor of the HP synthase, it's just not going to do anything in state 4. So you're not going to see any effect. So don't expect it to do anything. There's no rate control by HP synthesis in state 4. But it'll have big effects in state 3 because half of the control over this rate is exerted by the various components of the phosphorylation system. So this is the place to look if you have something that you think is changing complex 5. And looking in the basal rates is a waste of time. It's not going to do anything because there is no control in these other states by the HP synthase or by the adenine nucleotide count. So this underpins all of the experimental design for how you use a seahorse. You need to arrange the conditions so that you set it up so that the thing you care about has the most rate control. And then you measure the effect on oxygen consumption, and you can find out if your manipulation changed the thing you care about. Or inversely, if you don't know what you care about, you do the experiment blind and see which one changes most. And that tells you crudely where it's working in the system because it's the one that your particular process is controlling the strongest. So I think I've said all of these things, that the flux control coefficients measure how strongly something, a particular step controls a rate or a variable within the system. It varies depending on the conditions. So after you've added your oligomycin, the control is all shifted around. So you now get different control coefficients after your oligomycin addition than you did before your oligomycin addition. And the things you care about, looking at various modulators, will have stronger effects under some parts of the system and weaker on others, depending on how that step that they hit is controlling the thing you're measuring, the potential of a respiration rate. So design your experiments to make sure that the thing you care about has a strong effect on the thing you're measuring. And if it doesn't, measure something else or care about something else. I said all those. And then just to finish up, really just some illustrations to show you where one can go with this if you do what I did and go down this rabbit hole for a decade. As David mentioned, when you use the oxygen electrode, you can measure what's going on in cells in terms of the mitochondrial electron transport chain, just as well as you can in isolated mitochondria. So in cells, you have other reactions that consume oxygen, but when you inhibit the electron transport chain, those other reactions don't notice. They just keep chugging away. So you can subtract off the non-mitochondrial respiration, which in most cells is about 10%, varies a bit with cell type. And the residual amount is all what the mitochondria are doing. So in a cell or even in an intact animal, if you set up your experiment correctly, you can measure the aggregate rate of all of the mitochondria in that cell or in that tissue or in that animal. So that's really powerful. You can measure the electron transport chain rate in aggregate in your system just using an oxygen consumption assay. And in cells, you can also measure the mitochondrial membrane potential. There's a bunch of pitfalls, which David will talk about, but it can be done, and we did it in this example. And then you can just do the same titrations I was talking about. So here we have a liver cell, a primary rat hepatocyte, and we put it into state 4.0 by adding oligomycin. And then we titrate out with a respiratory inhibitor, and we can measure the kinetics of the proton leak in these intact cells. So we can take a hepatocyte out of a rat, and an hour later, we can tell you the kinetics of the proton leak in those liver cells. We can also take those cells and make them go fast to put them into something in the direction of state 3. We make them go fast by asking them to make glucose and urea, which is what hepatocytes are good at doing. So they're consuming a lot of ATP for these biosynthetic reactions. And we shift up the curve towards state 3. And we can now do two things. We can quantify in that rate how much of what they're doing is being used to make ATP. It's the bit that isn't the proton leak or the non-mitochondrial respiration. So it's about 70% of the total respiration in this particular cell model was being used to drive ATP synthesis. There's still quite a lot of proton leak in those liver cells, even though they're making ATP as fast as we can get them to make it. They're still doing about 20% of their respiration is just driving their proton leak, and about 10% here is non-mitochondrial. And by extrapolation, by doing that experiment in a bunch of different tissues, I extrapolate it to you, my audience, and say, as you just sit there quietly, probably you're spending 20% of your breathing just keeping your proton leak going in your mitochondria. And that's by construction from a bunch of experiments of this sort in various isolated tissues, and hoping that your tissues behave the same in vivo as they do when we put them in a dish. And then the second thing you get is you get the elasticities, you get the slopes of these lines. So you can do the full control analysis also in these cells and say what's controlling respiration in a hepatocyte, and how much is it the proton leak in the basal state, in the state 4.0 where we forced it with oligomycin, or in a fast ATP turnover state approximating state 3, or at least in the direction of state 3. So we can fully understand what controls the rate of respiration in the seahorse, because we've done these experiments in various cell types and we know on aggregate how cells behave and what's controlling the different parts of the system. So it's very powerful. You go to your seahorse and you understand why the rates are what they are, what controls those rates, and why they change when you do things. And that allows you then to interpret anything that makes a difference to those changes, such as your genetic modulation. This is an example of the same experiment now done in perfused rat muscle in situ. So we leave the muscle inside the rat, we hook it up to electric stimulation so it contracts. We measure the respiration rate by electrodes upstream and downstream of the muscle. We perfuse the poor animal with oligomycin, which before it all dies, it puts the muscle into a state 4.0, so we get the point here. We measure the potential by dye distribution, and we can titrate out before everything dies with either more contraction or less contraction to give us the substrate oxidation kinetics, or by titrating the electron transport chain to get the proton leak kinetics. And we get the same things. We get, in a fully contracting muscle in rat, how much of the oxygen consumption is driving ATP synthesis, about 60%, how much is driving proton leak, about 30%, how much is other, the stuff we can't inhibit with cyanide. And we can also do the control analysis based on the slopes of these lines. And again, in what's now approximating in vivo, it's an in situ perfusion of an in vivo system, we can fully understand the control of oxidative phosphorylation under our specified condition. And then just kind of fancifully to finish up, I was describing a system with one intermediate, the proton metaforce, and 3 modules, the substrate oxidation, the proton leak, and the ATP synthesis module. But there's no limit to the number of intermediates and modules you can analyze. The equations get more complicated, so you have to use matrix algebra to solve them, but it's all completely mathematically soluble from the rate and flux measurements. So in this system, we took hepatocytes, we measured all the stuff we thought was interesting and we could measure, like the glucose-6-phosphate concentration, the pyruvate concentration, the NADH-NAD ratio, the ATP or ATP-ADP ratio in the cell, the mitochondrial membrane potential, and a bunch of fluxes like how fast are they taking up oxygen, how fast are they putting out lactate, how fast are they converting endogenous glycogen into glucose. So the glycogen is outside the system, it's inside the cell, but the system boundary has glycogen as outside it. So this boundary only approximates to the cell boundary, it's not exactly the same. And we can measure all of these fluxes. We can do the titrations, we can measure all of the elasticities, and we can calculate all of the control coefficients and fully understand in our liver cell in a test tube or in a dish how OXPHOS is being controlled and how it's controlling all of the other variables in the system. And this shows the way that we can output that sort of information. So it takes a while to orientate yourself here, but here because we have so many different variables, we have control over each of those variables. So if there are 9 variables, there are 9 plots like this one for each of the variables and how it's controlled. So I'm choosing one of the variables, which is how fast is pyruvate oxidized to NADH in the mitochondria. in these hepatocytes and what's controlling that. And this inner circle of arrows shows what's controlling it, the control coefficients of the different blocks in the system, the different modules in the system over that rate. And the black arrows mean that they stimulate it, and the red arrows mean that they inhibit it. And the thickness of the arrow tells you how strong the control coefficient is. So this thick black arrow tells you that the component of the system that most strongly controls how fast pyruvate is oxidized to NADH is the mitochondrial phosphorylation system, the ATP turnover by the mitochondria. Other things also control it. So how fast is the cell demanding ATP? How fast is lactate being produced? How fast is glycogen being broken down? They all have some control over this rate. But the dominant ones are the rate of the pyruvate oxidation, sorry, the machinery of the pyruvate oxidation itself, or the machinery of the OXPHOS system. And then the outer circle breaks each of these arrows down into their components. So when mitochondrial phosphorylation is controlling pyruvate oxidation, how does it do it? Well, it does it by increasing the protomotive force. That, of course, increases the ATP, and that inhibits it. So within this black arrow, there's a thicker black arrow and a relatively thick red arrow. So there are opposing effects going on. When we stimulate this, it both stimulates through the membrane potential effects and inhibits through the ATP effects. And the resultant of all of the different changes is this one. We do the same thing in all of the others. And some of the blocks, like pyruvate oxidation, if in a hepatocyte you increase the amount of pyruvate dehydrogenase, it doesn't do very much. And the reason it doesn't do very much is that although you have a big direct effect, what that does is to increase the protomotive force, and that through these other things like the NADH and the acetyl-CoA shuts down the pyruvate dehydrogenase again. So it ends up having some control, but not as much as you expected because of all these feedback loops. So the point of going through this is to show you that by a relatively simple experimental manipulation, you can fully describe the control of this system. And if you're interested in PDH, you can skew your analysis to look at pyruvate oxidation and PDH and what it's controlling and how it's controlling it. If you're interested in glycolysis, you can do it that way. If you're interested in a different output, you can do it that way. But all of these things are accessible by experiment. And it kind of makes me burst into tears when I read paper after paper that says, we knocked out enzyme X or gene X, and it controls life, death in the universe. No, it's one component in the network. And under the particular conditions of assay that you're using, it had quite a high control coefficient over the variable that you're measuring. But it's not the only thing that controls your variable. This control is shared by a whole bunch of other things, which is why your group in one country can get into exciting scientific arguments with somebody else's group in another country who say, no, my process is controlled by this other thing, as if those two things were mutually exclusive, but they're not. They share the control in any one condition. And if your lab uses one condition and their lab uses a different condition, you can both be right. They can both be almost rate limiting because the conditions are different and control shifts around depending on the conditions. So once you understand that, you tend to be more friendly towards your competitors because you realize that when they get the wrong answer, it's not really wrong at all. It's just that they're setting up the system differently. And their answer is in fact right under their conditions, assuming that their measurements are right. So you're more sympathetic to them and you also understand your own data better and the constraints that you've put on it, like should I include Martin in my description of my muscle OXPHOS, how those constraints affect your answer. And that's why you get a different answer from the guy in the next lab, because you included Martin in your system and he didn't.
Professor Brand, is there any kind of a standard rule that these are all the things to be considered when we are doing this assay so that there can be this variability between the labs or the experiments can be minimized?
Yes, so if you're trying to solve a particular scientific question, you need to set the system up in a way that's the most effective to address that question. So I may have one particular question, the next lab may have a slightly different question. So we're going to set up our systems differently, and we're going to get different answers which are appropriate to those questions. The problem arises when we get into the same room and we try and talk to each other, and we now have diametrically different views of what's going on. And under that condition, you probably want to have some standardized condition. So some of you may have seen that in the mitochondrial field, there's a big consortium which has been trying to standardize the assays for mitochondrial function so that we can all talk to each other. And I think it's a valiant effort, but because the experiments you're doing are always contingent on what question you're trying to answer, you won't actually adhere to that norm for your particular system, but maybe it's helpful to have it so you can always redo your experiments in the standard conditions so you can talk to the person in the next lab about how to compare your results. So it's not as if there's a proper answer or a correct way to do it. It's rather that there are a multitude of different ways and you need to set it up in a way that's the most useful to what you're trying to achieve at the time. And that'll be different from the way that somebody else sets it up.
Thank you.
The danger comes when you don't understand that and you set it up by some standard method and it's not appropriate for your question. So you end up measuring something which isn't sensitive to the thing you care about, and you end up with the wrong conclusion that we've disproved our starting hypothesis, but the thing we care about controls this variable. Not necessarily, because you might have just looked under the wrong condition.
Thank you.
Okay, so I think this is where I finish up with my take-homes. Isolated mitochondria are really good for mechanism. They're nice and simple, and I applaud their use for mechanistic studies that don't try and do physiology in isolated mitochondria. The ammeter reports rates, and those can be really informative. And in general, if you had a choice between only measuring the rates or only measuring using the voltmeter, the potentials, in general, fluxes are more informative for most questions than the levels of intermediates. So I would rather use a seahorse than a fluorescent microscope for most questions in bioenergetics, but I would much rather use both. And then you realize the extension of that argument is if you go to Metabolon and ask them to measure all of the metabolites in your system, you're measuring forces. You're using a voltmeter, you're measuring the chemical forces, the concentrations of a bunch of stuff, and you're not measuring the fluxes. So you're getting the second best sort of information for understanding your system. And using isotope traces is actually much more informative than metabolomics in understanding fluxes in networks. It's just more of a pain to do, so people do it much less frequently. But it's the much better method in principle for understanding the rates and the information and matter flows through networks. If you only take from this that there are ways to analyze control, and it's not just an airy-fairy concept of, oh, my thing is controlled by this other thing, but actually you can be precise mathematically, then that would be good. But if you take more than that home, that, and if I really care that much, I should try and think in the way that control analysis thinks, that would be better. So control analysis reveals how control is distributed, and once you understand either mathematically or intuitively how the control is distributed in your particular system, you can then design experiments which focus that control on the step you're interested in. So David introduced his talk by saying, how can you use a seahorse to measure all these different things? How can you use it to measure the activity of the sodium pump? The answer is if you set up your system so that how fast the sodium pump in the plasma membrane hydrolyzes ATP is the thing that has the dominant control over respiration rate in your system, and there are ways to achieve that. Then you can use a seahorse to measure the activity of the sodium pump in the plasma membrane. But if you don't set up the conditions that way, but set it up in some other way, then your respiration may be utterly insensitive or almost completely insensitive to the sodium pump. And you can manipulate the sodium pump as long as you want, you just won't see any effect on respiration. So you really need to understand how you're setting up your experiment so that it's set up to answer your question. And once you do that, it can be really powerful to do it. And if you don't understand that, you can miss things that are really important. and you can misinterpret things that are really important. So if you think the rate limiting step is on X, but it's really on Y, and then you do your manipulation and the respiration rate changes, you'll publish a paper saying X changed. Whereas in fact, it might be that your manipulation was changing Y, and that was what changed the respiration. So the errors go in both directions. You can miss things, but you can also falsely interpret things if you don't have a good sense of what's controlling the different rates in your system. So as you go forward into the other sessions, a lot of what we're going to be talking about is that design and the interpretation of designs to understand what's controlling the rates in different parts of the system. And therefore, when you manipulate that system, why you see a change in this rate, but not a change in this other rate. And you can use that in the end to identify how your manipulation is impinging on OXPHOS, or why is it causing a dysfunction when I treat my rats with cyanide and they all die. You could answer that question using a seahorse. And then finally, I mentioned that hydraulic analogies are really good. And we gave this lecture a couple of years ago in the Buck, and one of the participants, Wayne Willis, who's at the University of Arizona, after the event, sent me these slides of what he'd been doing that summer in his backyard by his pool. So I think these are Wayne's kids, or the next door kids to Wayne's kids. And what they did was to build a hydraulic analogy of oxidative phosphorylation. So you have an infinite fuel supply supplied by a hose coming from the tap somewhere, which provides you fuel at a particular potential. That's the height above the ground. And that fuel then flows through dehydrogenases into the NADH pool. And obviously, as the NADH rises, then you shut off by mass action or by designed, evolved kinetics. You shut off the supply of fuel. So as the NADH goes more reduced, the dehydrogenases come near equilibrium and eventually stop, so you don't put more electrons into the electron transport chain. So the height of this water column here, if you can see it, is a representation of the redox state of the NADH pool. And down the other end, down here is oxygen. So the difference in height between the NADH pool and the oxygen is the delta EH across the mitochondrial electron transport chain. Here's the electron transport chain. It's got a tap in it, so you can inhibit or activate the electron transport chain. And that's driving the protomotive force. So here's the height of the protomotive force connected to the redox energy by the electron transport chain. And at equilibrium, once you account for the stoichiometry of the number of protons pumped, here it's 1 because the currency is water, then the height of the NADH pool and the height of the delta P pool will be the same. So at equilibrium, these will come to the same value in terms of the delta G of the reaction with a stoichiometric correction. And because this tap is partially closed, the delta P is slightly less than the NADH. So this is a real system with a flux through it, where there's always a slightly higher delta G or potential for the upstream than for the middle, than for the lower component in the system. And then the delta P is driving ATP synthesis. So somewhere in here, there's a water level for the ATP level, which is again slightly lower than the delta P. It's ignoring the conversion factors of the number of protons pumped to make ATP. I'm sorry, here's the delta G on this one. This is just the background. So here's the complex 5 and the machinery that goes with it, the adenine nucleotide translocase with a tap on it so you can turn it up and down. He's got it partially restricted so that the delta P is higher than the delta G for the ATP reaction, and it's driving that delta G. And if you increase the activity of the ATP synthase machinery, then the delta GP would come to the same value as the delta P. And in particular, if you stopped all the fluxes, so if you close this tap here, which is the ATPases that are burning this ATP, then all of these three would come to the same level as the system backed up and was in true thermodynamic equilibrium. But Wayne is clever, so he built in various leaks in the system. So he has a proton leak here, where if the delta P goes too high, you have a spillover. So you can never reach equilibrium because the proton leak always leaks some things away. And you also have leaks from fuel up here. And it's even cleverer than that. Around the other side is the cellular creatine kinase system. So we're looking from the other side. Here's the system we were just talking about with the electron transport chain and the ATP synthase. Here's the delta GP pool. And on the other side, he has a variable capacitance creatine kinase pool. So in most cells, as David will talk about in his lecture a bit, there's a creatine kinase that takes the energy of the ATP-ADP ratio and converts it into the creatine plus phosphate ratio. And that's a high capacity pool, so it's a great big volume. So if you have an active creatine kinase, as the delta GP and the ATP system builds up, it gradually fills up this pool. And then if you shut off ATP synthesis by the mitochondria, this can reverse and refill the delta GP of the ATP system. So the creatine kinase system is able to buffer the ATP level. And in a contracting muscle during a sprint, for example, in the aerobic phase before the sprint, you fill up your creatine kinase pool with energy. And then as you sprint, you can't get enough oxygen into your muscle to run the electron transport chain fast enough. So instead, you switch on the creatine kinase pool, you drain energy from here into your ATP pool and use that for your race, for your anaerobic 100-meter sprint. And this is a big pool, so it doesn't run down during the sprint, but it will eventually run down. And if you train, what you do is you change the capacitance of this pool. So he has an adjustable capacitance, and if you take that out, you can double the capacitance of the pool. So you just have this great big pool of creatine phosphate instead of a relatively small pool. So that's why you go to the gym, is to change the size of this adjustable capacitance pool. So I think it's quite instructive to go through that hydraulic analogy. If you understand the model, you probably understand the whole of this course really well. So if you have an idle moment later on this afternoon, stroke evening, stroke day, then just go through the model and see if you can understand all the bits and see how they're holding together. Because if you do, you'll understand all of David's thermodynamic lectures, you'll understand my control analysis lecture, and you'll understand the practicals and things that we're going to do a bit later. Okay, any questions before we wrap up this section?
Yeah, I had a question, Martin.
Yep.
You know, could you put up that slide on the different factors that are important for, you know, you had a slide where different factors could come into play to that might influence the hepatic respiration, and you had like factors like glycogen and all that. Yeah, but yeah, this one, right? So I was just trying to understand, like this would change a lot depending on the cell type, and my question was more related to if you want to capture the glycogen, how does the sample prep allow you to get more an analysis of the glycogen breakdown? Like, what would you have to do to capture that? And I'm guessing that differs between we're studying this in astrocytes, and how would you study that if you had that question?
So two parts to it. How general is it, and how would you do it for a particular pathway? I'll take the second one first. So this analysis did have glycogen breakdown as one of its variables. So the rate of glycogen breakdown to provide glucose, which either got oxidized or was dumped from the cells. We measured all of those things. And then we can, from the way we set it up, we can measure the effect of any of these blocks. So the rate of ATP hydrolysis or the rate of pyruvate lactate dehydrogenase. All of these, we can work out the control over the glycogen breakdown. So we can analyze for all of these specific modules that we identified, we can analyze how strongly they control glycogen breakdown.
And you're adding your exogenous enzymes to break down glycogen, or you're relying on the endogenous enzymes in the cell type to break down glycogen?
Endogenous. So these are primary hepatocytes. We don't starve the animals before we make them, so they're full of glycogen. And then during the experiment, they break down their endogenous glycogen using their endogenous machinery. And we're asking, how does the proton leak affect that? How does the electron transport chain affect that? And then the first part of your question was the generalization. So I kind of glossed it, but the analysis, there's two ways to look at it. The analysis is only true for the particular condition that you analyze. And in principle, as soon as you move even 1% away from that condition, everything might change. So it's not valid for any other condition in the same cell type. And it's certainly not valid for a different cell type. But then the part of that that is less discouraging is the thing I mentioned from irreversible thermodynamics. And that is that on the whole, these systems are well behaved, biological systems are well behaved. So the displacement from equilibrium roughly controls the rate. And therefore the structure of control actually tends to be more stable than you might have imagined. So you can extend out further than the infinitesimally small and still be reasonably true. Whether you can go into a neuron or not, you'd have to do the experiment to find out. You can't necessarily carry across the information.
Right. And
So
this,
it's very powerful, but it's limited by those constraints. It only applies to what you measure.
Right. And just to add further to this dialogue, have people looked at interaction between two cell types? For example, I'm just thinking about the astrocytes and the neurons talk to each other, right? And the astrocytes are providing the substrate. Have people co-incubated two cell types to sort of understand the same sort of this analysis, but sort of also include the cell-cell interaction in that?
That's interesting. No, nobody has done that. At the time that this was a very active area, the area of cell-cell interactions was considered esoteric and too difficult. But these days, it wouldn't be that difficult to do because we have the tools to measure what's going on in two different cells in a mixed population using microscopy, for example. So it could be done. And actually, it modularizes really nicely. So you could ask questions like, does the rate of glycolysis in cell A affect the rate of hormone production in cell B? That would be a very experimentally amenable question. So that would be an interesting thing to do. No,
and then just can you explain how? So, but if you co-incubate the two cells, don't you have the problem of all the inhibitors and everything going into both cell types? You'd have to find a specific or somehow physically separate the two cell types, or how were you thinking to look at the interaction?
Yeah, so the more complicated your system gets, the more your tools become blunted in terms of how you can make specific changes in one thing. So yes, you'd either do it genetically, which has got various problems of the time domain that you're working in, to change one cell and not the other one. Or if you had pharmacological agents that only affected one cell and not the other because of some isoform of some enzyme or something, you could do that. But you're right, otherwise you're affecting two modules simultaneously, which makes the interpretation difficult. All of those things can be handled, but it gets experimentally and mathematically quite complicated quite quickly.
Right. Thank you.
I take the lack of questions from everybody else to mean that you thought this was so straightforward and so easy that there's just nothing you need to ask because you fully understand it. Okay, let's take a break, grab a cup of coffee, have your breakfast or your dinner, and we'll be back for the practical session, which is you doing a lot more talking and not me. And we're still roughly on time, so let's keep the time and we'll come back at 3:30 from your session. So can you do that? Can you make it a 20-minute break, Ricky, or is that too difficult to do?
No, that's fine, but from 3 to 3:30, it was going to be with lab members.
I should explain, right. So when we come back from this breakout, you'll stay in those breakout groups to do the data handling. So part of our aim here is that you kind of say to the people in your group, okay, what do you know about? So you can answer all the difficult questions while I just take the simple ones. And we're seeding the rooms this time with members of my lab. So there'll be somebody there, you can look them up on the bios to see who they are, who ought to, and they won't admit to me if they don't, ought to know the answers and how to address those answers. And as I said during the intro session, their function is not to tell you the answers or give you tutorials, but to help you out if you get into a jam. So when we come back, you'll be going into those sessions. So I would take the breakouts as a chance to get to know that person and see what they work on and talk to each other and work out who's the one who's really works on this stuff and more able to answer it, and who's really lost, and we'll take it as an opportunity to learn something rather than an opportunity to answer the questions. And then, as you will guess, what we're going to do when we come back at various points during that practical session is I'm going to ask breakout room 2 to give me their answer to question 3, and then breakout room 7 to give me their answer to question 5, etc. So for each of the questions, each time, it might be you. So that's an incentive to kind of have a coherent idea amongst your group of what the answer to the particular question that's been posed is. So Ricky was saying maybe you need a bit longer. I've now waffled on for another 5 minutes. So that gives you 15 minutes to get to know people. So maybe she's right. Let's extend it out and start at 3:45. So let's make it a 30-minute break so you have a chance to do those things. And we'll reconvene at 3:45.